Welcome to the two of you. We'll wait for the other participants to join in. Typically, I try to start about maybe 3 minutes past the top of the hour to allow folks to start in. So go ahead, stretch your legs, grab some coffee. If you want to, you can get started downloading some of the prerequisites for the course, but I'll be walking over that with everyone once they come here. So just hang tight and I'll see you soon.
Hey, good morning, guys. This is Amit.
Good morning.
Hey, Matt. We meet again. I was in your last class.
Yeah, I'm glad to see you again and glad to see Vish again. Some familiar faces from previous courses. Welcome, everyone.
Good to see you.
Hey, Vish. Let's see, how many folks do we have? Oh, nice. We're getting Welcome, everyone. Looks like we're starting to gain a quorum here. I believe we're supposed to have about 15 participants. So if you don't mind holding tight for just 3 more minutes, give everybody a chance to start up. I threw a timer on my screen so that way you know how long you have to grab a cup of coffee, stretch. In the meantime, if you would like, you could go and start downloading the materials that we need for this course. They're all listed on my screen, and I pasted them into the chat so you could check those out. I'll bounce back to this and help make sure that everybody is set up before we really dive in earnest to running the code. This is very familiar to those of you who are with the earlier trainings, but see you in about 2 minutes. All right, great. Welcome everyone to the parallel computing training. Thank you all for joining us. It looks like we have a good crew here together with about 12 to 15 of you, which is awesome. So glad to see all of you, some familiar faces from previous trainings and around the Julia ecosystem. So it's nice to see you all. Oh, nice. Looks like the last few participants are just hopping on now. Perfect timing. My name is Matt Bauman. I'm the Director of Applications Engineering at Julia Computing. I wear many hats at Julia Computing, from product team sorts of things for the products that we're building at Julia Computing to the open source development of Julia itself, with which I've been involved over the past 7 years, to the training materials and trainings that we're doing today. So it's a lot of fun for me. Training is one of my most enjoyable tasks of all the hats that I wear. I enjoy them. And the parallel computing training is one of my most fun courses. It's a real deep dive into how parallel computing works in Julia and touches on kind of how modern infrastructure works as well, because in order to really understand what you do in Julia, you need to understand the hardware as well. And so there's a lot of topics to dive into here. And there's a lot of different ways in which you can do parallel computing, which makes this a challenging course to do in just 2 days. There's lots of topics to cover, and it can be kind of confusing on all the different flavors of parallelism that exist. Some actually are parallel, some say they're parallel on the tin, but aren't actually parallel. So we'll go through all of that, try to demystify it all for you, and hopefully have an enjoyable time. Just a little bit of setup from the get-go, some understanding of how this course will be run. So we have 2 days, today and tomorrow, 4 hours each day. I like taking 10-minute breaks at the top of each hour or so, plus or minus 10 minutes. So I also like trying to make sure that the lectures that I go through, come to a conclusion. So sometimes we'll stretch a little bit here or there. I ask for your flexibility as we do so, but you can count on, plus or minus 10 minutes from the top of the hour. We'll try to take a 10-minute break to give you all a chance to take a breath, or stretch your legs, refill on coffee or water or tea or whatever your beverage of choice is, and reset your minds to come in for the next topic. And during those breaks, I want to stretch my legs as well, but I'm also happy to stick around for parts of them, answer any one-on-one questions with setup details or things that may not be fully applicable to the class at large. Often when I do that, I like doing it in the chat box, just so that way those of you who leave don't feel like you're missing out on anything, and you can feel free to leave. The other little bits of administrative things is this session is being recorded. So if you have to step away at any point, I will send out those recordings to the participants afterwards, and you can always come back and review. Or if you missed something or misunderstood something, you can always come back. But really, I encourage you to ask questions as we go through, as we set things up, and as I dive in. This entire training is interactive, which means that I can stop at any point, go down an alley, go down a little diversion, and I enjoy doing so. I find those to be the most fun and engaging times during these courses. And generally, we find that folks have better experiences when they're in courses that people ask questions. So don't feel like you're taking away from others' experience by asking questions. In fact, you're adding to it. Generally, when one of you has a question, it means that many of you do. And so encourage you to ask questions. I'll keep the chat box up on my computer, but you're also welcome to dive in on voice. Sometimes that can be a little awkward though, but always, don't feel ashamed. I think we're all getting used to this virtual meetings. I found that the class classes that we've been running. We've been running these courses for the past 3 years, but in the past year, in the past 6 months, folks have been more adept at jumping on the voice chat or the chat box, and now that we're all getting used to remote work these days. So with that, looks like we have the full crew here. That's awesome. I want to make sure that you are all set up to run. So the way that we're going to run through our course materials today is with Julia version 1.5. That's the latest stable release of Julia. If you go to the julialang.org/downloads link here, you'll see the stable release here as 1.5.2. That's what you want to download for your given platform. It's pretty simple install on all 3 platforms, be it Windows, Mac, or Linux. Fairly straightforward. Encourage you to follow, just use the defaults because that'll make the next steps a little bit easier. You'll note that there's also the option to download the long-term support release. Often we get questions like, can I use that instead? What's the difference between these 2 releases? And the key answer here is that, you know, the stable release is fully supported, and we'll be using a few features in our training materials that have been introduced since 1.0. So as Julia matures and gains new releases, these 1.4, 1.5 releases, they add new features that are backwards compatible, but they're not available, of course, on Julia 1.0. The long-term support release is really geared towards companies and individuals that have very stringent production requirements of things not changing, no new features and things like that. The one thing to look out for, though, is that we'll likely have a new long-term support release with version 1.6, which hopefully will be released around the new year. And so by training you all on the current stable release, we're getting you set up for the future. And so even if you do require a long-term support release for your own company or things like that, you know, this will get you, you know, pointed in the right direction at least. And like I said, the current released version of Julia is always fully supported. It's just that once 1.6 comes out, we'll expect you to upgrade from 1.5. We don't want you to stick around on 1.5 forever. So that's the distinction there. So once you have Julia installed, you will install the editor that we'll be using, which is Visual Studio Code. Again, you can click the link. I copied these links into the chat box. Hopefully you can see those there and click on them directly there, so that way you don't need to type these out. But Visual Studio Code, again, totally cross-platform, and you can download for your given, you know, whatever icon fits your system here. Again, just follow the defaults. You'll be in good shape. These things have gotten much more robust lately, and we've had much more success getting folks installed. Then lastly, there's a plugin that allows you to you know, integrate Julia and Visual Studio Code. Visual Studio Code is in fact a totally language agnostic IDE, and it stands for Integrated Development Environment, and can be used with really any language. And so you can add Julia as the supported language, and that's what we'll do here. I'll come back to these last 2 steps. I think we'll jump in to a brief discussion about parallel computing and kind of get our feet wet, so you all can continue working on these steps if you want. But I'm going to go over a little presentation about, you know, what's happening with parallel computing and things like that. Yeah, let's pause just a moment for any setup questions that you have. One of you asks about, you know, is Julia Pro 1.5.1, is that going to work well, or how can, you know, what should I do there? Julia Pro is built atop a different editor environment. So your screen will look a little bit different than mine. The commands that you'll run will be a little bit different. You can totally run through the materials in Julia Pro. But instead of being based on, this is Microsoft's Visual Studio Code editor, it's based on GitHub's Atom editor. It's just a different architecture. Both work to run Julia quite well, both look somewhat similar, but we find that Visual Studio Code is looking to be the future. And so in the near future, we'll likely transition Julia Pro, which is Julia Computing's Julia release that kind of tries to bundle together these 3 steps into one download, make it a little bit easier to get things moving. That will move to Visual Studio Code as well. It's something that we're a little bit slow to do because we want to make sure that this is fully robust and fully stable before we do this. I wanted to move these materials to Visual Studio Code ahead of time for several reasons, one of which we'll see tomorrow. And we will, it's because you can actually run Visual Studio Code in the cloud, which makes for some really fun parallel capabilities that aren't accessible on your local machines, likely. Anyways, it kind of depends. And so I would encourage you to follow these instructions, even if you already have Julia Pro installed, simply because yeah, they can live nicely side by side. In fact, I currently have about 15 different installs of Julia that all happily coexist. Some Julia Pro, some Julia, some open source, all sorts of different versions. And they all coexist just fine. They take about 200 megabytes of space, so it's not that big of a deal. So yeah, I encourage you to download this. And if you have an older version of 1.5, say 1.5.0, 1.5.1, or 1.5.2, that's fine. Don't worry about updating. You may want to update. They have some bug fixes that are nice, but it's not going to change anything with what we do in the course today. And yes, just to reiterate, the courses will be recorded, or they are currently recorded. You can see, I think, in your windows, the flashing red light that says that they're being recorded, and we'll send those out afterwards. It takes some time to process the 4-hour recordings, so often we won't send them out until next week, I think, is generally the way that works. All right, any other questions here before I talk a little bit about what parallel computing is and means and does, and how things look in the shape of the ecosystem these days? All right, well, let's dive in. So a big question here is what's happening to our computers? What's going on? How are computers becoming the faster? Oh yeah, the slides I don't have on GitHub. I could print these out to a PDF and send them along with the actually, you know what? I should just put them on GitHub. I'll convert them to PDFs and just throw them on GitHub. So that way, this evening you can look over them as well. That's pretty straightforward to do. So yeah, I'll put them on GitHub. They're not there yet. They're just on my local Google Drive right now, but I'll share them all with you. So, one of the key reasons for a parallel computing webinar or training is because our computers are requiring parallel computing these days. Up until the mid-2000s or so, chip manufacturers, the heart of a computer, right, the CPU, were able to keep jamming more and more and more transistors onto a single chip. And importantly, this meant that they could keep increasing, as they did this, they were shrinking the size of the transistors, which meant that they could keep increasing the frequency of the chips, which meant that they could keep increasing the single threaded performance of the chips. And so I really like this graph because it kind of shows how these, these 3 different things or 4 different things have progressed over time. So the orange triangles here, those are the number of transistors, and this is a log plot, right? And so it's been exponentially increasing, the number of transistors that we can jam on a single chip. And this is something that a guy named Roger Moore, who was the head of Intel at the time back in 1965, he noticed, and he said, hey, you know what? I bet we'll continue doubling the number of number of transistors we can fit on a chip every 2 years for the next decade. Which we're all used to hearing, right? That's Moore's law. And that is something that we've heard so many times. It's, chip speeds, and often it gets kind of morphed into chip speeds doubling every 18 months or so. But really what he was talking about was the number of transistors. And that had for a long time correlated nicely with speed. The one thing that I think gets lost a little bit is just how profound of a statement that is. Exponential growth isn't something that we see very frequently. It's not something that we see in many ecosystems, many places. It's not something that we see often, and it's not something that we see unbounded for a very long time. If we were just to, take this same sort of statement and apply it to something like speeds, right? To the speed of travel, say. And if I were to say, every 2 years, I'm going to double how fast I can move around the world. How many doublings do you think I could go before I would hit the speed of light? The answer is that it's not that many, right? So you start off walking maybe about 3 miles an hour, jogging at 6 miles an hour, then 12 miles an hour, maybe on a bike, 25 miles an hour. Sorry for those of you who are kilometers per second, but the basic premise stands, right? So 25 miles an hour in, maybe on a horseback, 50 miles an hour in an automobile, 100 miles an hour in a fast car, 200 in like a Formula One, 400, 800, you just keep doubling. Well, after about 15 doublings, we've hit the speed of light. It doesn't take much to hit the speed of light there. And 15 doublings, that's just 30 years. And in over 30 years here, if we're doubling every 2 years, over 30 years, they were able to keep jamming on these transistors at a very constant exponential rate, right? This is a log plot, so a straight line means that they kept going at the same pace. And it held true. Not only did Rogers Moore's statement back here in 1965 hold true for the 60s and early 70s, like he had initially said, but it held true for 40 years. Which is wild. I don't know. I just don't think that gets enough appreciation about how Moore's law has really shaped our industry and shaped what we do in computing. And so for a period right in the 90s or 2000s, it didn't make sense if you had a program that would take 2 years to run. Well, just wait 2 years and it'll take half the time, right? And so there's this constant trade-off. You kept looking to the chip manufacturers to just speed up your code automatically for you. And it was a great time. It was lovely. Everything was going smoothly. But then something happened around 2005, which is the chip manufacturers hit a wall. They suddenly topped out at the frequencies that they could push the chips to, around 2, 3, 4 gigahertz. That was the extent, right? I remember buying a computer back in 2005 that was 2 gigahertz, and my computer today is 2 gigahertz. That's not changed in the past 15 years. The chip manufacturers have still kept jamming more and more transistors on chips, right? Up through, this graph goes through, I think, 2018 or so. What's happened, though, is that those transistors no longer are improving single-threaded performance. You can see that the single-threaded performance here in blue kind of plateaued. There's some small gains here and there, but really it has not gone up with the transistor counts, along with the frequencies of chips. So where are those transistors going? What's happening with those transistors? Why do we keep jamming more and more transistors onto single chips? Well, the answer is that they're now being used to increase the number of cores. So starting in 2005 or so, chip manufacturers started putting multiple cores on a single chip. Instead of trying to throw more transistors at single threaded performance, they were then saying, hey, we've hit a wall here, we need to start moving to multiple cores. And so lots of folks love proclaiming the death of Moore's law, at least up through 2018, though. It's still charging ahead exactly like Roger Moore said it would back in 1965. It's just we're not seeing the performance returns that we used to see. So that's driving really why parallel computing and HPC in general, HPC standing for high performance computing, has just been, such at the forefront of computing over the last decade, because no longer can we just do everything single threaded or wait 2 years for our single threaded programs to get faster, because they won't. We instead need to work as programmers as ways to express our algorithms that can be done by multiple processors at the same time. So to get the best performance out of our hardware today, we really need parallelism. And this applies not just to your computers, but also your cell phones. They have multiple cores these days. Every device just about has multiple cores. And so no matter where you are, no matter what you're doing, parallelism is required to get the most out of your hardware. So that means that computers today have single processor cores, and as chip manufacturers have thrown more and more transistors at single processor performance, it's meant that our single processor cores, even though a single core, a single node, like a single logical processor, that core can actually do more than one thing at once, which kind of breaks a lot of abstractions that we have as programmers that kind of think of a core on a processor as just being able to do one thing at a time. That's not true at all. They can do lots of things concurrently, but they try to do it in a way that kind of feels like it's single threaded to a programmer. But then, you have lots of those cores on a single chip, and you can even have multiple chips, multiple processors. So in a single box, these days you can have 48, 50 cores on a single chip, on multiple chips ganged together, that you can have, hundreds of cores available to you that on a single box. But then you can, of course, network multiple computers together and exploit compute across lots of computers. You can kind of think of that as being in a computer lab and having all of the machines in the computer lab churning away on different subsets of your problem. And that's exactly what a cluster is, right? Is lots of boxes networked together with very high bandwidth interconnects. And then even beyond that, there's a fourth layer here where our computers can actually have specialized compute hardware beyond the standard CPU. You can have other hardware attached to your computer that can churn away at particular problems faster. So examples here include GPUs, which, as the acronym says, it's a graphics processing unit, but it turns out that they're also really good at matrix multiplications in general. And so they've kind of grown into their own device class beyond just driving graphics into what are called general purpose graphics processing units, or GPGPUs, that then can churn away at problems much more efficiently. Some classes of problems, we'll talk about that. There are also even more specialized pieces of hardware. So for example, Google has their own extension of kind of what a GPU does. They call it a tensor processing unit, or TPU. There are other things. So for example, if you're into cryptocurrency, there's specialized compute hardware that can mine cryptocurrency, right? because they've designed a dedicated circuit that can do that faster and better. And so you offload it to other compute hardware. It's the same kind of concept. You have a specialized compute hardware that you interface with, communicate with, and get answers from. So computers today are complicated, right? There's lots of different ways in which you can do parallelism. And so that extends not only to from our laptops, but it also extends to the fastest supercomputers in the world. Just this summer, there's a new #1 slot here in the fastest supercomputer in the world. There's a list called the Top 500. You can go to top500.org. It's kind of a fun place to explore and just kind of see where these are the biggest parallel systems in the world, right? They are the most complex, most largest rated systems in the world. And you can dig in to kind of see what exactly these are doing. And some of them, in fact, use all of these sorts of forms of parallelism together all at the same time. So if you look at the #2 system here, this is the fastest system in the United States and had been #1 for a very long time up until this summer. It mixes all of these forms of parallelism in a single cluster. So this cluster has 4,600 nodes. You can think of those as boxes, kind of, sort of. They're very specialized boxes and don't actually have complete, hardware around them, but you can kind of think of them as separate boxes that are connected by networking to each other. Each one of those boxes has 2 processors. That does has multiple processing, and each one of those processors has 22 cores. So each box has 44 cores of processing available to it. But then also each box has 6 GPUs. So if you want to, make the most use out of this Summit system and you're programming on the Summit system, you need to do what's called heterogeneous parallel computation, where you need to split your data set and your project and kind of your algorithm across all 4,600 nodes, right? And you want to divide it up so that way the data can get to all of these different boxes and can churn away. So that's one form of parallelism. Then within each box, you want to use all 44 cores using multi-threading. So that's another form of parallelism. And then at the same time, you want to offload compute and use the 6 GPUs that are available for each node. And so this is a crazy kind of system to work on, right? If you want to get the best performance out of this, you need to use 3 different forms of parallelism and have them all working together. The #1 system is a little bit different in that it doesn't actually use GPUs. Instead, it uses a very specialized ARM chip, the same kind of network architecture that's in iPhones and Android phones, these ARM chips, but it's a very specialized ARM chip that kind of sort of, morphs the kind of bridges this gap. It kind of makes a fuzzy gray area between a traditional CPU and a GPU, where it has lots and lots of SIMD units. And we'll talk about how that looks a little bit later on. But that's how they do this. And they do this amazingly without GPUs. And with lots and lots and lots of cores, 7.3 million cores available to use. So it's fun to look at this list. I like pointing to it just so that way you have a sense of what is going on here and how these things work. But you can see this #1 system has lots of nodes, way more nodes than the Summit system did, way more processors than the Summit system did, but no GPUs. So instead of leaning on GPU processing, it instead uses a specially constructed ARM chip that has very, very wide and large SIMD that kind of sort of acts like a GPU. So This leads to some challenges, right? Whether you're on a supercomputer system, which you likely are not, or your own laptop, or a cloud system, right? Today we have access to cloud resources where we can actually spin up lots of boxes in the cloud, connect to them via networking and exploit them. And you can actually build your own little cluster to an extent that has never really been possible before. But this leads to some challenges, right? You absolutely need peak performance, because when we start talking about parallel code, you're really talking about real money. It's no longer that you've bought a computer and it's just sitting idle and you're, you want to use it the most you can. Well, once you start talking about, for example, cloud computation or cluster usage or other forms where you're using lots of machines, well, that's real energy use, that's real hardware use, and it's real money. And so you don't want to spend a lot of time doing this, right? You want to have the best performance and you need a fast language for the biggest benefit. Another challenge comes from how we've learned as programmers. Historically, we've been taught, and have learned how to reason about programs serially. That is, we think of a computer stepping through executions, instructions incrementally, right? You just go on and on and on down a list, and the computer will just do this and maybe loop, right? And you have a loop, but you have this mental model, or at least I have a mental model of an instructions pointer that's just like pointing at the line of code where you're running right now, moving around, and you can only have one of those, right? As soon as you have multiple things that can get out of sync, you need to start reasoning about where all your execution is currently happening and what's changing where. So we need to think about how we express parallelism. And importantly, we need to think about it in ways that are safe, that is thread safe. I'm sure you've heard of that. And without race conditions. That's another core concept that we'll talk about in how we structure our programs. So that way, we can write our programs in a way that we know exactly what the execution is doing at any given point. And at some points, we'll say, hey, you're free to parallelize this. At other points, we'll say, hey, you need to come back together and we need to go back to our kind of traditional serial mental model here. Another big challenge is that, well, if you have a big parallel computation task, often that parallels with large data sets, right? The reason that you have a large compute problem is because you have a large data set. And so you need to consider carefully data movement costs, right? No longer is it just the compute cost, but also just simply moving your data around can be expensive, both in terms of real dollars and cents, but also in terms of time. Lastly, and kind of what I started off this little mini lecture talking about is how there's so many different hardware configurations, right? We've already seen 4 or 5 different ways in which you can express parallelism, be it single node, this multi-thread, multi-machine, GPU, TPU, all these things. We need to think about what strategy or strategies potentially will fit our system and our problem. And so, of course, our answer here to the first question is Julia. It is a fast language that allows you to express your computation efficiently and at a high level. So that kind of tackles that first part. But it also tackles some of the other parts as well, where we have built into Julia lots of these parallelism, in fact, all of these parallelism strategies available for use. And that's what we're going to be going over today, is walking our way through all of these strategies. The course, as we have it outlined, the first lecture that we're going to do is actually going to be on serial Julia performance, kind of to tackle this first bullet point on our parallel challenges slide. We need a fast language. And so we need to use Julia, but we need to use Julia efficiently. And so the very first lecture here, I know you are all in a parallel programming course, but I found that this to be a beneficial thing to kick off the class with, is starting up Julia serial programming and how we efficiently express Julia and get these things up and running as efficiently as possible. So that's where we'll start. And the reason for that is because, let's see here, I think, nope, not that one. Let's see. I wanted to get to here. This is a nice case study where we were able to get Julia running on one of these top 500 supercomputers. At the time, it was a top 6. It's the Celeste project. I know you've heard us talk about this. It's something that we're very proud about, is that Julia is the only high-level language that's been granted coveted cluster access time to hit what's called a petaflop, which is a trillion computations in a second. It's just a huge computational task, or trillion, quadrillion. I can never remember how many my SI prefixes are there. But it's a huge computational task and was able to express it efficiently because we used all the tips and tricks of Julia high performance. And so this is one example of how that looks. With that, I think I'll pause my lecture there. We have a bunch of overviews here in terms of how we go about the parallelism strategies. We'll talk about these as we get to them. But let's kick off with our high performance Julia talk. So that way, because really, if you're a slow single threaded program and you parallelize it, well, you're just paying more to run a slow program. and sure, you might see some speed ups, but it's better to optimize your serial program first, because then you will gain you're starting off at a better point, right? So parallelism at its core can really only do twice as fast if you have 2 machines, 5 times as fast if you have 5 machines. And so if you move your baseline faster, well, then you can drastically increase your 5x performance, for example. There's limitations there, but that's the main reason why I start with fast Julia code. So with that, let's take a break from our slides. Thanks for bearing with me for that short little presentation. I hope that helps us get set up for the day. With that, I want to check back in. How are folks doing on this installation task of getting everything installed and up and running? I'm going to launch Visual Studio Code here and pull that up. So I have, actually, let me just close this out and launch it from scratch. So I've already installed Visual Studio Code, and we can create a new window here and bring that over into, oh, oops, I want to be full screen, that's why. So when you launch Visual Studio Code, you should come up with a screen like this. This will be how you can get started, begin working with our lectures today. The key third point there, so hopefully you've already installed Julia, you've already installed Visual Studio, and you are at a screen like this. If not, harangue me on chat. I can stick around during our first break and help anyone get set up that are having trouble. The key third step is linking together Visual Studio Code and Julia. To do that, you click on the extensions icon here on the left. It's kind of this funny 4-square icon that kind of, I don't know, represents extending a 4-square. I don't understand why they think this looks like an extension, but that's the icon they use for extensions. And you can see that I have already installed the Julia language support. If you've not installed this yet, you won't see this listed under your installed tab. And so it's just as simple as typing Julia into the search bar. It'll pop up as the very first result here that has all of the tools that you need in order to to run Julia code, there'll be a little green install button that you just click. Once you click it, that green install button will change into a restart button. You need to restart Visual Studio Code to fully load in the extension. You can click it and it'll automatically do that for you. So I've already done this step, so I can't demo it from scratch, but hopefully that's simple enough that you click the green install button on the Julia and then reload. Once you have that installed, then you should be able to pull up your Julia REPL, as it's called. So the main interface for Visual Studio Code, it takes a little bit of getting used to, is through what's called the command palette. And you can access that through the view menu. And the very first item here is the command palette. You can see that on a Mac, the keyboard shortcut is Shift Command P. I believe on other systems, it's Control Shift P. So on Windows or Linux. That's going to be the main interface for running things within Visual Studio Code and kind of the main way you interface with it. It's really nice as a programmer to have this kind of command line interface to my editor. I like it a lot, but it lacks in discoverability, right? If you don't know that this thing exists and this thing is there, it's really hard to navigate around Visual Studio Code. So I'm going to open up this command palette. You can see that it has a bunch of commands here, including my most recently used commands. And so you won't have these if you've just installed this. So you can just type Julia REPL, and that will bring up the commands to start what's called the Julia REPL. And this is how we can launch Julia and get things going. You may see a pre-compiling statement there if that's the first time you do it, but it shouldn't take more than 10 seconds to load up and get a Julia prompt. And once you have a Julia prompt, well, you can execute Julia code to your heart's content right here. And this is what's called a REPL. That's an acronym for read, eval, print, and loop. So what it's doing is it's reading the Julia code that I wrote in, it evaluates it, gets the answer, prints out the answer, and then loops back to the starting point. And so now it's ready, waiting for me, waiting to read in more Julia syntaxes that I can type in here to evaluate, print, and loop. Let's see here. Okay, so that's how we can get this started. And now I have VS Code interfaced with Julia. That was the third step in my little 4-step process here. The last step is to add a folder and to get going with our training materials. Perhaps the easiest way to do this, starting from a blank screen like this, is to click on this files icon and hit clone repository. And this will bring up a repository, a URL or some way that you can grab the repository source to clone and to essentially, what it does is it downloads it to your computer and starts tracking your changes, which is really nice. It uses Git, which is this version control software. I encourage you to learn it. It's a very powerful tool that we use throughout the Julia ecosystem. It's a great programmer's tool to prevent the kind of situation where you just keep renaming files and you end up with report final, report final, report version 7 final kinds of version control. So encourage you to check it out. It's simplified my life significantly, but it is a little bit complicated. You could have a whole 1-hour course on Git, but that's beyond the scope of today's lectures. So I'll grab my training materials. So those are, I can copy this and I'll paste it into the chat here so you can all get that, just copy and paste it directly. But I can just paste it directly into here and clone it. This will download it to my computer, start a new folder, and start a new session for this. And maybe I'll just do that, sure. It'll ask me where I want to clone it. And so I can create a new folder, let's just name this, what is this, 2020, 1029 parallel. Sure. So that will clone this in. And then once I've cloned it, it'll ask me, hey, do you want to open this? And yeah, I do. I want to open this and start working in it. So that opens it, gets it going. And in here are all of our course materials. So that is the process to do this. I think we're getting towards the top of the hour, which is perfect. You can see once you're in this this environment, we can go in here and check out, for example, the README. And this is essentially what those slides were that I went over this morning already. This README talks about how, it has the same graph, talks about all those same things that I talked about, but is a little bit more rough bullet points of the key things that I wanted to talk about there. The last thing that I want to do is, let's start that REPL again, get this up and running. Now, this will, I have this inside, let's see, oh shucks. Yep. So I want to, shoot, I should have done this slightly differently. I want to move into my parallel folder here. So by default, when you start a Julia REPL, it will launch inside your, in the folder that you have set up here. So this is, how we've set this up. This is where I am, but all my materials are inside this extra folder here called Parallel. I'm working on consolidating all of our training materials into one repository. So eventually, all of these instructions can be consolidated and made a little bit simpler. So I want to actually move inside of this Parallel folder in order to do that. Jean-Philippe asks a very good question. I hope I didn't mispronounce your name too poorly. Asking, how do I get to a shell command prompt? And that's a great question. Sorry about that. The answer here is by typing a semicolon character at the REPL. It will change what's displayed to be shell, and then I can write not Julia, but interface with my computer's shell directly. So on a Mac, that's your terminal. On a Linux, it's your shell. On a Windows, I think it's your cmd.exe by default. You can interface with it directly. And so you just type a semicolon, and if that semicolon is the first character on your line, then it'll change your what's called the REPL mode. So that's one REPL mode. It's really handy. What I'm going to do here is I'm going to change directories into my parallel course. So I can use the cd commands to change directories into this parallel course. So that way I am, my Julia REPL and my current state is in this. And so then I can ask for a list of all the files using the shell mode. I could do this with Julia commands as well. And instead of using the shell, as I've started up in my training folder here, I can use Julia commands to just say cd parallel. And that will change directories. And then I can read dir is the Julia equivalent of these things. So you can do these either way. I often use the shell for things like that. It's a little bit easier. And if you're familiar with it, great. Otherwise, this is the Julia syntax that you can use. Yes, thanks, Michael. That's where the Git repo is for all the trainings. Okay, so the last thing that I want to do before our break is to add all the packages that we're going to use for this course. So that's why I had you all, once you've started your VS Code REPL in the training course, I want you all to move into the parallel folder. So that is just, this CD parallel command to move into the parallel folder. And then I want you all to instantiate your environments and activate them. So this is using Julia's package manager. And inside this folder here, you'll note that in the parallel folder, let me make this a little bit bigger for you all. Too big. That's pretty good. So inside of this parallel folder, I have two special files. So these are all the courses that we'll go over, starting with course number 20, 30, 40, 50. For some reason, I thought two-based indexing seemed appropriate here. I don't know why, but we'll start with serial performance and move on there. So that's what our first lecture will be in the next hour. But additionally here, beyond the README, there are these files called the project and manifest. These are Julia's files that are automatically generated that keep track of all of the packages that are used throughout this course. So what you can do in order to, use this course and reproduce exactly this course without much consternation is to go into the package manager mode. So kind of like the shell mode, there's a package manager mode that allows you to speak directly to Julia's package manager. And the way you get into that is just by typing this close bracket character at the REPL prompt. And again, just like the semicolon, if it's the first character on the line, you'll see the prompt change to a PKG mode. Now, by default, it will show that we are in this global environment for Julia version 1.5. And that's what this means. This is the default environment for, every time I start up Julia, that's going to be the environment that I start up with unless I've passed in additional options. What I want to do is I want to change this environment to the parallel course environment. That is, I want to change it to an environment that has all of the packages that we'll be using today. So I'm going to activate with the current directory. So this period is kind of a shortcut for, hey, let's activate this current directory. That's why I had you change directories into the parallel folder. So that way we can activate the current directory as our package environment. That'll say, hey, I'm activating this environment, this package environment that knows about what all the packages are that we're going to be using. And it's the environment in this project.toml. So this project.toml is this auto-generated file that keeps track of all of our dependencies. I can ask Julia, what's the status now? So what all is here? If you do this, you might see some text saying that these things aren't installed, that you've not installed these yet, but it knows that these are the required packages for this course. To install all these packages, I then just type instantiate. So the two commands there are to activate your current folder, right? Because we've changed directories into the parallel. And then this is, of course, at the PKG prompt. So you want to be in the PKG prompt to do that. And then instantiate will download all the packages, get them all set up on your computer, not just these packages, but also all of the dependencies. So in addition to these dozen packages or so, you'll probably see about 3 dozen or 4 dozen more fly by on your screen because this will be the first time installing them on your computer. They've already been installed on my computer because I was just testing this out myself. So I didn't need to do anything to instantiate this environment, that is, get this environment up and loaded. The last thing that I'll ask you all to do before we go on our break is to just type precompile at the PKG prompt. And that will go through all of the packages, get them ready. So that way we don't need to spend time during our lectures and hopefully speed up a little bit of the subsequent work that we do. So I'll just paste that in here too, into our chat. And with that, I think we're now at the top of the hour, like I had promised. I think now is a great time to take that first break. I'll stick around if there are any questions on the setup or basics of parallel computing. I can take those, and we can hopefully make sure that everybody's in a good shape to run this code and get going. So then we'll talk about our next 3 courses as we go. All right, to do the 10-minute timer for our break, I like pulling up a 10-minute timer just on Google because that's a nice little easy UI that I have always open. I'll reset this. And so that'll put us at about 8 minutes past the hour, and I will reconvene then. So I'll start my timer now and see you all in 10 minutes. All right. Welcome back, everyone. It sounds like a lot of you are having success getting things up and running, and that's awesome. There's a handful of folks still having some trouble. During the chat session, there were a few questions. One was, I expect you to see a warning message saying that you can't import some compiler thing into wrap or something like that. Yeah, here, I had the same warning as when I precompiled everything. That's expected. That's part of the magic that our machine learning architecture does, some compiler magic that does, I don't know. I think we're working on getting rid of that warning, but for now it's expected and doing what is supposed to be happening. So hopefully you'll see something like my screen. You'll probably see more packages that got precompiled than what I did because I've already compiled most of my packages, but this will get things set up for you. A few of you had trouble, if you're using Julia Pro, you'll just need to delete this manifest. So you can just right click on it and delete it and then go through the steps that I showed you, and that should work, instantiate, and then it'll use Julia Pro's packages. The last error that I was trying to debug with Syed here was how it's having trouble installing all of these things because there is some what's called a resolver error, and that's what happens when you have incompatible versions of packages installed. That shouldn't happen here. It's a little puzzling to me because they are explicitly compatible because it's what I'm using, right? The project and manifest encodes exact versions. In fact, it can be kind of interesting to just peek inside what these auto-generated files are. These are the top level dependencies that we'll be using. So we'll be working our way through these packages as we go through things. The manifest is what has the exact versions, right? And so this manifest should be able to automatically instantiate. My hunch is that Syed has a few extra packages in his global namespace that, or his default global environment that aren't cooperating well with this set of packages that I have in my environment. If anyone else is seeing that error, please let me know and I'll try to debug it. I think Syed, if you're okay, I'll come back to that during the second break and we can try to debug it a little bit farther there. And yeah, we'll see if we can get this working for you a little bit later on. But I think in interest of time, let's dig into our serial performance. We'll, yeah, hopefully get Syed caught up a little bit later on during our next break. But let's talk about, getting Julia running efficiently, so that way once we add parallel multipliers to our code, we're actually starting with a big number or a fast number, hopefully a small number really, that we can then multiply out and get a really nice performance speed up by parallelizing it. So a lot of this comes from the performance tips chapter in the manual. So if you're not very familiar with Julia itself, this is going to be somewhat of an advanced course. We're going to be talking about lots of advanced topics in Julia and things. So the Julia documentation at docs.julialang.org is a great place to get started. And for advanced usages, some of my favorite chapters in the manual are at the very end. And that includes these performance tips. That has lots of really, really nice examples of how to write high-performant Julia code. Follow this, this document and you'll be a Julia expert in no time. There are also a few other really nice things at the end here, like workflow tips, a style guide, noteworthy differences from other languages. These are some of my favorite chapters in the Julia manual. I encourage you to check them out. I wish I should submit a pull request to kind of like try to emphasize these a little bit more because they're hidden at the bottom of the manual right now. You have to scroll all the way down to find them, but they're awesome chapters to look at. So we'll go through some of the examples of how to, some of these main concepts of writing high performance Julia and getting them, getting your Julia code running fastly and quickly. The first thing to use and to think about is to benchmark, right? If you need to measure your Julia code in order to know at the outset whether you're slow or fast or somewhere in between, and you need a baseline to understand, hey, am I parallelizing things? Are things running quickly? Are they actually working here? And so you want to experiment. It's very easy to experiment in Julia, and that's one of the awesome things about our REPL, is that it's a really nice experimentation platform for doing all sorts of experimentation. What we'll be using is the benchmark tools package to benchmark our performance of a single threaded program to get an understanding, hey, is this running quickly? So yes, if you're in the PKG mode and you're stuck here and you hit enter and you just keep getting in, it's a sticky mode. It'll stay in the PKG mode. And of course, if you try to run a Julia command here, it'll say, I don't know, that's not a package command. I couldn't figure that out. To get back to a Julia prompt, just hit delete. And you can kind of think of that as deleting that invisible close bracket character that you typed at the beginning of your prompt. So close bracket to go into PKG, delete to get out. There's also question mark is a very helpful one of these modes that we talk about, where it'll give you help. And so you can ask for help on all sorts of things in Julia. And this is a helpful thing where, if I were to try to write a Julia command here, well, it'll try to figure out what should I give you help for? And in this case, it'll give me help for the plus command. And so this is a nice other mode of the REPL where instead of evaluating it as Julia code, it tries to evaluate it as some question that you're asking, like, what does this do? But again, yeah, same idea. If you're in the help prompt, just hit delete to get out. So let's benchmark start with some benchmarking, come up with some basic function that we can play with and gain an understanding for. When you're in an editor here, so the way I opened up this editor, right, was I, opened up my file pane. I'm in my training folder that I had opened after cloning it. And you can click on the notebook where we are here to open this. I'm going to close this back up in interest of screen space. And then once we're here, you can click on a single line and hit Control Return. That will send that line to the REPL. So you can, we have these, set up here to run and execute nicely. You can select a bunch of code. So I can select a whole bunch of things here to execute at the REPL and just hit, let's see, I think Option Enter will execute that entire code block. And it'll run the entire code and give me the result of the answer. So there's lots of ways of doing this. You could also grab this copy and paste it down here, or you can just kind of incrementally do this with Control Enter. Just hit Control Enter and it'll send one line at a time into your REPL and do it that way. So that's how you can evaluate things. What we're going to do is we're going to define a Julia function. This is a very, very simple Julia function that gives us, which element in some array, some data set is closest to a given point, right? So I have this function. Now I don't have, there's lots of great finding functions in Julia, but they're all, for exact matches or things like that. So the way that you would interface with Julia's standard library might be something like this, right? Where what we want to do to figure out, which element is closest to our given point is to look for the absolute distance from between our data and our point to give us a vector of all of the distances, right? And then find the minimum distance. But we're not asking for what's the minimum distance between our data set and our point. We're asking which index or which element is the closest to our point. So we get the index of the minimum distance and then return the value at that index. And so this allows us to then, create some data set that's, say, a 5,000 element long data vector that's uniformly distributed between 0 and 1, and just ask, hey, what is the value of the data point that's closest to 0.5, right? And you can see that it's something that's very close to 0.5. We generated lots of these, so you'll find something that's pretty close here, right, to essentially our needle in the haystack. So this is one way of defining this function. So how long does this take, right? That's a key question in optimizing your code is, I want to see how long is this going to take? Well, built into Julia are a bunch of little introspection things. This time macro is what it's called. It starts with an at symbol, means that it's a macro. And if you hover over the symbol in VS Code, it'll pop up with some help. And you'll see that it evaluates the expression and then prints out how long it took to evaluate it. So if I send this to my REPL, you'll see that I got the same answer that I got before, but I also get how long it took to give me this answer. And you can see here that it took about 23 microseconds to do. So milliseconds, microseconds, 23 microseconds to evaluate this. And if I do this a bunch of times, you'll see that it's a little bit variable, right? Here, this time it took 100 microseconds. This time it took 50 microseconds, 46, 50. There's some variability here. And it kind of depends upon what's happening in my computer. That it's a pretty quick evaluation, right? 50 microseconds. So there's some noise here. And I really want to get a better sense of how fast is this, right? Is it 100 microseconds? Is it 50 microseconds? How fast does it take to actually do that? And actually, if you look at the help string for time, they'll actually point you to the benchmark tools package to evaluate these things and avoid the noise of measurement and kind of try to sample that out. So you can, because I've already said at the top here, using benchmark tools, I have access to this fancy benchmark macro, which will, when I do this, it's going to run this lots and lots and lots of times in order to see, how fast this was. So remember, I was seeing numbers anywhere from 20 microseconds to 100 microseconds by using the time macro, just timing one iteration of this. The benchmark tools benchmark macro here, it actually evaluated my function 10,000 times, and then gives me a distribution of how long did it take each time, right? You can see that the fastest execution time that it got was 16 microseconds. The median time was around 33. The average was 42, and the maximum was a whopping 8 milliseconds. So this is how you can start digging into the performance of your Julia code. And this works for small things, it works for big things, and it dynamically changes the number of samples it takes depending upon how big of a function you have. I believe it tries to target about 10 seconds worth of sampling. So if you have a large function that takes a long time, it might only evaluate it a handful of times. And that's okay, because there's also going to be less noise, measurement noise, and other things the computer's doing because it's evaluating for a long time. There are a few other things to note that get printed out here. You can see that in doing this algorithm, we actually allocate some memory, right? We've allocated about 40 kilobytes of memory in order to execute our code. We'll talk a little bit about what that means and how that works. You can also see that sometimes we end up spending time in what's called the garbage collector. And so the garbage collector is something that's always running in Julia and running behind the scenes. And it'll collect any trash that you generate as you work in, do your algorithm. And so if you don't generate any trash, well, then there's nothing for the garbage collector to do and it won't run. If you do generate trash or scratch space or arrays that aren't necessary in the output, well, then the garbage collector will need to clean those up every now and again. And so you can see that when we are taking the longest, really, it's not our algorithm that's taking the time. It's rather that, you know, our garbage collector had to peek in and say, oh, hey, you've generated quite a bit of trash here. Let me clean this all up. And it's halting the execution of our program to do that cleanup. And you know, so in our maximum time here, so the evaluation that took maximum time, you can see this. If you see what was just posted in the chat, you know, it looks like you're just one step ahead of me. We'll see what that looks like in just a second. That's on the profiling section. So you've gone one step too far there in your evaluations. We're just looking, so you just want to click on the benchmark tool and hit Control Enter. I guess if you might see that output if you hit Shift Enter. I guess I am missing. So kind of annoyingly or confusingly, there are two modes of sending data to the REPL here. If you hit Control Enter, it'll just copy, it's essentially copying this line to the REPL and evaluating this. If you hit Shift Enter, it'll evaluate the entire cell, and a cell is marked between these funny comments with the hash %%. So unfortunately, it looks like I messed up my cells here and I should have an extra hash %% in between these two sections. So I think what you were seeing is that you're hitting Shift Enter, which would evaluate the entire cell, and this next section on profiling gets evaluated there. So yeah, I don't like the Shift Enter evaluation for two reasons. One is because it's not totally obvious where these cells start and end, right? It's just kind of, I've tried to mark them as best I could as I was going through this, but I missed this one spot. The other reason is that it doesn't show up down in your REPL. I kind of like the very clear, history here where you can see not only what the output was, but also what the input was. And so Control Enter will put it in your history, something to keep in mind. All right, so that's benchmarking in a nutshell, all the different things here. There's lots of depth and that you can dig in to kind of see this. But the core understanding here is that we now have a ground truth, right? We understand what our performance profile is. And in the best case, we'll see something around 16 microseconds to run our algorithm, but it is generating some trash, right? It is allocating some memory and doing its, in getting its answer. It's allocating 40 kilobytes of memory. Which means that sometimes the garbage collector needs to get run, which means that on average, we'll probably see a performance of 40 microseconds or so. And if this were a key portion of your algorithm, finding the closest data point to some given needle or some given point, if that was a key portion of your algorithm, you would want to optimize this, right? You'd want to make sure that this is not doing any superfluous work, because you could actually speed up your algorithm twofold or maybe even threefold if you were to get rid of some of the variability here, or even more so potentially if we could optimize it further. Then if this was a key bottleneck to your algorithm, well, this would be a good place to tackle and dig in. So how do you know where your bottlenecks in your code are? Well, that's profiling, right? That's the other side of measuring the performance of your code, and that is profiling. I'll get to Syed's question about the dollar symbol in just a second. It's a little idiosyncratic thing in benchmarking that we'll talk about in a subsequent section. First, let's talk about profiling, because this is how we kind of gain an understanding of what we need to optimize, right? And where opportunities for optimization might live. So we'll use the built-in standard library called Profile, pretty straightforward. This profile.clear just makes sure that we're set up at a good place, and then we'll profile our algorithm. And what this does is it kind of peeks in during the evaluation of our of whatever comes after it. So again, we use a special macro starting with the @ symbol in the profile, and it essentially just profiles everything that comes after it, right? It'll do what's profiling. And so what is profiling? Well, profiling just means that Julia will keep tabs on the execution. It'll peek in somewhat randomly as we're executing our code and just ask, what are you doing right now? And in order for it to gain a good understanding of what's happening, because this happens somewhat sporadically at a given interval, you can actually adjust that, but that's a bit more of an advanced topic. Because it peaks in sporadically or occasionally, we need a large corpus for it to evaluate. And since this find closest function doesn't take that long to execute, let's just create a little dummy for loop here that'll just evaluate my find closest function 100,000 times or so. So this is just a simple dummy for loop where we don't even care about what the iteration step is. And we just use an underscore to say, I don't care what this is. We're just going to do it 100,000 times. And this gives me time, right? Because this would take, if I use the time macro here, it would take about 5 seconds or so to evaluate all of those 100,000 iterations. And so this just gives me a chance for my profiler to peek in and see what's happening. So as it does that, it collects all of the back traces or the locations in code where we were as we were profiling. And you can ask the profile standard library to just print those out, collect it up for me, so that way I can see what was happening. And goodness, it prints out a lot of gibberish. This is what E. Furtak was seeing in this next section. It's a lot of gibberish that gets printed out. You can kind of see it prints out some things. The key parts, there are 3 key parts on each line that get printed here. The first thing is the number. This is, remember how I talked about what happens during profiling? Julia is peeking in and asking, where are you in your execution profile? What function are you running right now? And the number here is the number of times that we peeked in on Julia's execution, and it said that it was in this function. And so what makes this a little bit complicated about doing at the, interactively here is that we're actually deep inside, Julia itself, and the infrastructure to run Julia code is in Julia itself. And so the first, say, 15 or so lines here are all just kind of the basic infrastructure for running code from VS Code. And so everything that we run will have this kind of shared structure of, coming from this start function, coming from our Julia function, running the REPL, getting things going. So you can see that the next line of code here is where we were in our code base, and the third is the function that we were running. So you can, follow this stack trace the whole way down. So we started Julia, running the main REPL, doing all these things, running the VS Code server, evaluating these things, including, and then finally, down here towards the bottom, we are in our code, right? So here you can see that, at the 24th REPL command prompt on the first line, we are running some macro expansion. And then inside that, here finally is our code that we were using, right? You can see, where it was defined, what it was running, and exactly how this works. So now we can get a sense of, what proportion of time was spent in our own infrastructure, right? You can see that, of the 23,000 or so times that Julia peeked in on our algorithm, about 14,000 times were spent at line number 2, about 9,000 times were spent at line number 3, about 25 times were spent at line number 4. And then you can go even one level farther and see, what were we doing inside that function? Well, here, these 13,000 lines were materializing some broadcast. These next lines were in the find min, right? And this is inside the base standard library again. So that is where we, that's the architecture here. But of course, this is a terrible way to visualize this, right? It's nice and easy to print it out, but it's a terrible way to visualize it. What we can do instead is, because we're in a visual editor here in a GUI that has lots of really nice editor tools, we can do what's called a profile view. And this prof view is kind of the same idea as profiling, but it also will view it in VS Code. And this @profView macro is from VS Code. It's VS Code specific. So those of you who are using Julia Pro, this won't work for you, unfortunately. There are other profiler tools that you can use there. Like there's a pure Julia package called Profile View that you can do. But I like this one because it integrates in with VS Code. So let's run prof view instead of profile and printing. And the cool thing here is that this pulls up a graph in my editor, nicely arranged, that I can do all sorts of fun sorting with. I can look and see. I guess I need to zoom out just a little bit to see these things here. Nicely graphed. You can see relative times spent in different regions. I sort by the total amount of time taken, or the self time. The self time, that is the time in which you're not in any deeper function, right? That is the time that is available to optimize. This is a little tricky though, because you end up seeing like lots of the base built-ins here, right? So we're seeing that most of the time in our function is actually spent in set index. And if you reveal where that happened, well, it takes some time to get there until you finally find, aha, we were in our find closest function here on the first line of code. And so it's a little bit tricky to find this, and this isn't this is, there's lots of depth in terms of ways in which you can evaluate this and dig into your code, but this kind of has the opposite problem, right? Whereas when we looked at the profile thing, we saw all of the infrastructure to run the code itself before we got to our code. Here we're seeing all of the built-ins that implement our code, and we need to dig in to find our code here to figure out what the proportion of time is being spent in things. So how do we find that little nice middle ground of where things are? And a really nice visualization is to click on this little fire icon here. And this will open up what's called a flame graph that will show your entire execution. So we ran for 9 seconds here, and shows exactly what we were doing for all of those seconds. I can collapse this down into just kind of the single groups. It kind of, instead of showing it in the time view, it collapses it and merges together similar cells. When you click on this flame graph thing for the very first time in VS Code, it'll prompt you to install an extension. It's very quick to just hit install, and then you should see this, and you'll get what's called this flame graph. So how do you read this? So the first thing that I did, so I clicked this flame graph, and then I clicked this tiny little collapse button to collapse things down. And now I can find where in here I am, in the middle, that lovely middle ground that we're after, right? This find closest function. That's really what I want here, this find closest. I want to see, exactly, this is where I want to spend my time. And this is the function that I defined. This is the function that I can spend time figuring out. So you can see in my find closest function, about 60% of the time is spent materializing a broadcast, and about the other 40% of the time is spent in find min. And so you can see these are the 2 times that we have here in our function. And then you can dig down and see all of the infrastructure above it and below it in terms of the built-ins of Julia that evaluates the broadcasting and find min, because these are just pure Julia things, right? So you can see how much time is spent in the Julia code itself, as well as in the code that we've done. So this is how you can start digging in and understanding, how these things work. Flame graphs are a great way of doing it. And again, the key magic is just finding the middle ground of where our functions are, right? This is the code that I ran, this find closest, and then seeing what time is being spent within that function. These are the three cells that I really care about here, somewhere tucked in the middle: find min, materialize, and find closest. So let's go back to our definition here of what we defined and how we did that. So I can close this flame graph, make this a little bit bigger again. So this is what we wrote, right? This is the function that we had. We had find closest. We first created this scratch array of all the distances. So if I have 5,000 data points, I'll have 5,000 distances. And this is a brand new array that we're generating. We're subtracting out our data from our point, taking the absolute value of it and getting a scratch array. And then we're finding the minimum value and, importantly, the minimum index of that distances array, and then returning the data point at that index. So this is really doing 2 separate operations, right? And remember that this operation here, this seemed to be taking about 60% of our time. This operation here, this one took about 40% of our time, right? We were looping through, and importantly, it's creating junk, right? It's creating a junk array of distances that we don't need. We're just using as part of our computation. And in a traditional language like Python or MATLAB, this would be the fastest way to code this up, right? Because you're using, this is like the vectorized way of thinking about it. You're using the best-in-class tools that are available by our standard library, and doing this. But in Julia, we can do better by combining these 2 operations, right? There's no real reason that I need to first create 5,000 temporary values that give me the distance from a point, and then find the minimum of those 5,000 values, get that index and return it. I can do all of those things at a single loop, in a single pass through my data set. And the way that looks is just something like this, where we can create a new definition, find closest to, takes the same data set, the same point. But now I'm just going to write my own for loop that just loops over every element in my data set, finds the distance of just that one element, not all 5,000 at once, just that one element, and just asks one simple question: is this current distance from this current element to our point better than the best distance we've seen before? If it is, let's update our best value and our best distance. And then at the very end, after we've looped through our entire data set, we can just return our final best value. This is a really simple algorithm, right? Just 8 lines of code or so. It's a little bit more verbose than what we had, but importantly, this is kind of a data-driven design, right? We're caring about how we're iterating over our data. We're only iterating over our data once, and we're not creating any scratch arrays anymore. And this allows Julia to optimize this to a level that we weren't able to do before. And so we can evaluate that, again, send that to our REPL. And the first thing that you want to do anytime you do an optimization is you want to run your test suite, right? And so you can send, I'll just create a very simple spot check to kind of remind myself to tell you that, when you're doing optimizations are the best way to introduce bugs. So we want to add a spot check here. You of course want to use Julia's test suite and run your tests and make sure that, hey, doing this is doing exactly what we want, testing some edge cases as well and everything like that. You can see, yes, okay. So that is the same. And now we can benchmark this and see, are we doing better than what we were doing before? And sure enough, we're doing a whole lot better on my computer now. Instead of, what was it, 16 microseconds was our best case scenario time. Now we're down to 6 microseconds. So faster than twofold faster. And importantly, we're no longer allocating any scratch work here, right? We've removed that temporary array that took care of all of that. So there's no more allocations, which means that we no longer need to run the garbage collector. If you don't generate garbage, your garbage collector doesn't run, which means that our maximum time spent is a whole lot closer to our best case time. The variability here is only dependent upon what else my system is doing, not really Julia itself anymore. Julia is no longer in the way. And so that is how, how these things come out. So this ends up being much faster in the best case, significantly faster in the worst case, and much better, a much tighter profile that will be more consistent performance. So this is a good example of how Julia can optimize things. You'll note that I didn't put any types here. Julia is able to do this optimization and get this is giving me C-like performance at this point. This is the best kind of performance that you can get. You can test this out, use Julia's interoperability, see how fast C could do it, for example, but I'll ask you to take my word for this. This is giving you that compiled language performance that you want and giving you the best case performance that you can get. A question about how does Julia return true? Is it based on the output results? Well, the spot check here, I'm just asking, is this value the same as this value here with the double equals? And so it's saying, yep, that is true. That's the Boolean value that we use to represent that they're the same value. So that's what you'll see with the output. If you're using the test set, you can use the test built-in standard library. You could say, hey, let's test this, and it'll say that that test passed. This would be how you would do it as a unit test. It just makes sure that whatever you put here returns true. So yeah, it's based on what the output gives me. You'd want to test other values as well to make sure that the optimization is correct. This is just kind of a canary in a coal mine, right? So let's talk a little bit about macros to get to the questions that Andre and Syed were asking about, how this benchmark macro works and why are we using this $sign here? So we'll get to that in this section. So macros are these funny things that start with these @ sigils. They're kind of like introducing a new keyword to the Julia language. And what's really cool about them is that they're totally extensible, which means that other packages can introduce macros to do any Julia syntax. Essentially, they transform what you've written into other Julia code. So a really, really simple example here is the assert macro. So the assert macro is kind of like a very, very simple test that just says, hey, whatever comes through here, if it returns true, then we'll do nothing. If it returns false, so if you say 2 plus 2 equals 5, it'll throw an error. So this isn't the same, right? If I were to just evaluate this at the Julia prompt, it does something different and doesn't throw an error, but rather just returns false. So the assert macro is doing something special here. It's just kind of like a special keyword to the language that is, extensible and allows you to do some cool things. But all it's doing is it's essentially taking the code that you wrote and rewriting it into a different form. There's another macro called macro expand that essentially allows you to peek in to see how is this rewriting the code that I wrote. So you can see with the assert macro, it's taking the code that I wrote, and instead of evaluating the code that I wrote directly, it's instead evaluating this complicated if-else syntax here. And if I were to evaluate this, then this is exactly the same as running that assert 2 plus 2 equals 4. So if 2 plus 2 equals 4, then return nothing. Otherwise, throw an assertion error that said, hey, I was asked, does 2 plus 2 equals 4? And I got something that was different than that, right? So in this case, this is true, and so we return nothing. If I do assert 2 plus 2 equals 5, well, I throw that error. And again, I can ask what was the code that was generated by saying, what's the macro expand here? And again, it's just this for loop that's saying, hey, if 2 plus 2 equals 5, then we'll return nothing. But of course, that's false. So we end up in this else branch that ends up throwing this error that said, hey, we got an assertion error that 2 plus 2 does not equal 5. So we're going to throw an error in this case. All it's doing is it's rewriting the code that I wrote. And this can't be done in a function, right? Because I'm actually literally taking the code that I wrote and putting it in two places. And that's kind of some of the magic that macros can do, is they can work with the code that you write, and each macro can define its own special syntax. And so we'll be using macros extensively. We've already seen it for performance code, right? We've already seen the time macro. So you can ask Julia to time some evaluation. So I can time the sleeping for a second. And again, I can ask, what's happening, macro expand here. This is more complicated because it's outputting not just the code that I wrote, but so here's the code that I wrote. It's inside this jumbled up mess of lots of complicated stuff here. And before I evaluate my code, well, I'm getting some timing infrastructure. And after I wrote my code, I'm printing out how much time elapsed and things like that. And so it's transforming the code I wrote in some fancy way. The same thing happens with benchmarking, right? It's transforming my code to put it inside a for loop and evaluate it lots and lots and lots of times. We'll see these a lot in other things as well. So we've seen time, we've seen benchmark, we've now seen assert and macro expand. We'll also see some code introspection. And importantly, we'll use these for our parallelization primitives. We'll use these macros to kind of define sections of code that can run in parallel or not. It allows us to introduce keywords to the language that are extensible, right? They're not built in, but they're ways in which we can work with the language directly. So that talks about macros. And remember that we wrote this, and I told you, I promised with that find fastest to function or find closest to function, that this was as fast as Julia can be. And I want to talk just very, very, very briefly about how Julia does that, right? I didn't talk about types. I didn't do any types, but Julia behind the scene is generating specialized code for the types that I've passed in. So remember, this is the function that I wrote. It's this Julia function that I'm just copying and pasting it into a comment here so I can reference it. I can ask Julia with a special code introspection to add type information. And this is what Julia does when it runs. It will automatically add type information to my code and get it running quickly and rapidly. Well, oops, I didn't. If you just select code, sometimes you don't select the entire thing. Let me do that again. So I can ask Julia for its intermediate result here and ask it. So when I run find closest to with the data set that I have, that RAND 5000 and 0.5, what are the types that you'll specialize for? And so you'll recall this was the definition. And this is Julia giving me its intermediate results. And this is a little bit of a funny pseudo Julia syntax that takes a little bit of squinting to read, but I encourage you to make an attempt and kind of see how this looks. And sure enough, you can see Julia code, right? Our first line was best val equals first data, right? And sure enough, here is that first line of code. Importantly, now I'm asking Julia for its intermediate results when it calls this, and it's saying, I know that that's going to be a float 64, which is kind of cool, right? It knows when it pulls data out of my data set here, it pulls that first element out, that it's going to be a float 64. Never did I tell it that it was a float 64, but Julia can figure that out based upon the type of data itself, right? And remember that data itself is was a random uniform between 0 and 500. And I can ask Julia, so what is the type of data? And you can see that incorporated into its type is the element type. And so that's how it knows when it digs into it, it's going to have a float 64. And then we subtract out, right? We take the best value minus point, subtract that out. And this is an intermediate result here. We subtract out best value from a point, and it knows that the result there is going to be float 64. And this is what we call type inference, where Julia can walk its way down the entire execution chain of what you do. So the next thing that we do is take the absolute value of that temporary, and that too is going to be a float 64. Here you can see that data itself, it knows, is an array of float 64 and all on and on and on and on. This is how Julia is able to compile down to really, really good performance without me ever thinking about types, because it's able to do this, what's called type inference. And it knows all of these types the whole way through. It can keep going the whole way through and know on each step of the way, it knows exactly what types these are going to be, which means that when it compiles it to machine code, it can use exact machine arithmetic without ever asking, hey, what type are you? Which is the kind of question that Python tends to ask a lot, and is somewhat the reason why for loops in Python and other languages tend to be slow, because they need to ask these meta questions in the middle of your loop. Hey, what is this element, right? In the middle of this loop, Python or MATLAB would need to ask, what is this element that I got out of my data set? And how do I work with it? How do I subtract out of it? How do I do a subtraction with it? How do I then take the absolute value of that? Julia, right up front, based upon the types of the arguments that I passed in, knows what these things are going to be, and thus it can compile it down without those meta questions, without asking what type are you and how do I reason about you. And so that's what you see here. This is the kind of the pseudo Julia intermediate result that talks about all of these things. It's a little bit of complicated syntax, but you can kind of squint and make correlations between what you wrote. It really is, Julia itself here, but just with some extra notations. These special %2 values are what's called single assignment nodes, and they kind of work like variables that Julia uses to represent, variables, and so you can see that they get referenced later on, and so on and so forth. But it's pretty straightforward besides that point. And there's some go-tos here too, right? We don't use go-tos in our pure Julia code. This is a form that allows Julia to understand it and work with the compiler toolchain a little bit easier. So remember, that was entirely predicated based upon the type of my data, right? I know that I have an array of float 64s, which means that I know that my element type is float 64, which means that I know when I index into it or iterate over this, I'm only ever going to get float 64s back. I can destroy that by using a less well-typed container. So for example, I could have a container that just knows that it's going to be a real value. It could be an integer, it could be a floating point number, it could be a rational number, it could be a float 32, a float 64, any of these things, right? And each one of those would have different computer, like core processor intrinsics, right? The way your processor works with floating point numbers is a different instruction set than the way that it works with integers. That's just kind of how computer performance works, how our processors work. And so if Julia isn't sure what we're going to get back, that means that it needs to ask those meta questions. It needs to ask, hey, what are you, in order to figure this out? So you can see here that when I get my first value, so if I ask for this, again, this intermediate result, now with this new data where I have an array of reals instead of an array of float 64s, you can see that no longer am I certain what my first data point is. It might be a float 64, which is a subtype of real, but it also might be an integer. It might be, a rational number. To construct this, I splatted all of my elements into an array with an element type of real. So this ... There's a question on the chat about what this ... means. It's essentially saying, hey, let's take all the elements of my data set here, all 5,000 of them, splat them into a new array whose element type is going to be real. That's the Julia syntax here. It's a little bit of a funny syntax, and I don't encourage you using splat for this, but it's just kind of a simple way of changing the element type here. And destroying the knowledge up front when I call find closest to. Now I'm using this array of real values, and I no longer know up front what elements I'm going to get back. And so Julia, the way that it compiles these things is when you call a function for the very first time with a given set of arguments, Julia will compile a specialized version. So what specialized version gets compiled for this new data? Well, it's a pessimized version that kind of has to pessimistically ask before it does any sort of operation. It needs to ask, so how do I subtract out between this real value and a floating point number, right? This could use floating point arithmetic if the real value it got was a floating point number. It might need to convert an integer or convert a rational number, do something else in order to do this subtraction. And at that point, it just kind of throws up its hands and says, you know what, I don't know what the promotion system will end up giving me back. It might be anything at this point. And at this point, every step along the way before it calls each function, it needs to ask, what are you and where's the function? How do I take the absolute value of this intermediate result, for example, and on and on and on and on. So this is how you can start seeing, this is a lot of meta questions. Everywhere you see an any or a real, Julia has to ask, what are you? How do I work with you? And what functions can I call with you, including in your for loop? And so you'll see this with, like, as we benchmark this, if I benchmark my find closest to with my new data set here, you'll actually see very poor performance because inside my for loop here, we're now like a factor of 500. What is that? Yeah, a factor of about 50 slower because I'm asking meta questions about my data. I no longer can compile down to the float 32 or float 64 computer operations. I now have to ask every time I index into my array, what are you and what do I do with you? And this will give you Python-like performance in Julia, which is fine. There's good use cases for that, nice dynamic behavior. But this is such a common problem that we actually have a nicer version of code typed here that just simply says, hey, give me the warnings here. Just tell me right up front, are there any warnings that say, how I'm working about this, and it'll flag them in red then. And so you can just see the flags here in red as to where are these things that are going to be problems and where am I going to need to ask meta questions. And it's at all of these points where there's red flags in my algorithm that it's asking these meta questions. And so this is what's called a type instability, is the language we use in Julia for this. And in order to prevent that, well, you just want to make sure that, for example, your data structures are, are concretely typed. So you want a data structure like data itself, where it's an array of float 64s instead of an array of anything, or an array of some abstract super type. That will give you better performance there. You'll also see the same thing both with arrays, but also with structures. So if you're creating your own structures, you want the same sort of thing. And the most common place you'll see this is running things in global scope, right? Because if you're using some global, that global might change at some point, right? And so if you have some for loop at global scope, it needs to pessimistically ask, what are you? Because the global value might change unless it's constant. So that might change. And you want to be careful about functions that change what they return based on the values. You want to do that carefully. And there's a lot of details on that in that performance tips chapter. I know we're getting towards the end of my hour. I'm almost done with this section here. I want to talk a little bit about that benchmark tools special syntax that folks were asking about with this $sign and what this $sign means on the benchmark tools macro. So this gets to some of that global type instability things. So remember that macros, they just take what you write and change how it's written. So you can think of our benchmark tools macro as putting what we've written inside a for loop, inside a function potentially, and writing it exactly like what we have here. So if I were to do some very, very simple benchmarking of, say, the sign function, I want to take the sign of 0.5, but I pass it as a non-constant global, right? I'm at my top scope here, my file scope. So X here is a global value. It can change at some point down the road. So if I were to time sign of X here, well, remember, this is putting it inside of a function, inside of a for loop that is referencing this X directly. It's kind of taking what we wrote, putting it inside a for loop, and putting this reference to a non-constant global inside a for loop. And so that means that inside the benchmarking kernel, Julia is asking that meta question, what is X and how do I work with it, right? Because it's referencing this non-constant global that might change to, say, an integer, right? And then I'll get a different answer back and Julia will have to do some sort of promotion, and it needs to generate code that can handle that kind of type change, right? And it could even change to, say, a complex number, and you can take the sign of a complex number. And so it needs to be able to handle all of those permutations inside its benchmark code, which is asking that meta question again of what are you with that X and how do I work with you? That's often not what you want to measure, though, when you're benchmarking tools, because often, you'll want to not reference a global, but rather think of it as an argument that gets specialized with your Julia code. And that's what this special $sign does. So remember that our macros here, they can implement special syntaxes that, so let me go back to my 0.5 again, that treat your, they can interpret what you wrote as however they want to. And so when they see a $sign here, it's like a special flag that says, hey, let's treat this not as a global reference to the global X, but rather let's pretend that it was an argument that got passed into a function that's type stable that Julia can reason about ahead of time, which is often how you'll be writing your Julia code, right? Where you have arguments that are type stable that Julia can reason about. And so this is actually more representative of the kinds of performance you'll see out of the sign function. That's just like a handful of computer cycles, 5 nanoseconds or so that it takes to run this. Whereas if you look at the overhead of asking that meta question, there's about 20 nanoseconds of overhead. This isn't a 5x overhead, it's a constant 20 nanosecond overhead. So it's a really low overhead to ask that meta question, right? There's not much overhead here. But if you're doing some core numerics, well, that's going to become significant. So then the Vish is ahead of me here. On the next section, you can actually get better performance than you might expect without a flag, because again, the same principle applies. If you write a constant literal, Julia can do some form of constant propagation, constant folding. It knows it's compiling a specialized function where it knows that the value of what we're passing to sign is always going to be 0.5. So it can do some work right up front and just potentially even return my answer for me without ever doing the computation. It can pre-compute the answer essentially and give you even better performance. But again, if I flag it as an argument, I get the same performance as flagging X as an argument. And so without these $ flags, you can sometimes see faster performance than real world use cases. And you can sometimes see slower performance than real world use cases. In general, if you're timing functions, you want to put $ to flag just to remind yourself that, hey, these are going to be inputs and I'm going to allow Julia to treat them as though they're non-constant inputs as arguments to my functions. So yeah, it's a great question, but it all falls out of the same behavior. So I want to briefly talk a little bit more about some of the other intermediate results that you can ask from Julia. So typing is the first level of the stack. Then we use what's called the LLVM compiler architecture to generate what's called native code. And it's kind of cool that you can ask for all of these intermediate steps as you go through. And these are things that you don't need to know as a Julia programmer, but it's kind of nice to understand and kind of see what's happening. And we'll talk a little bit about LLVM code in our next section, because it can be helpful in understanding the performance that we're getting, because this is, you know, the computer instructions that our code is getting translated to. So if I ask, what is this low-level representation, this low-level command that our processor is going to run when I just simply add two integers, I get out this kind of gibberish here that is a function that adds I64s with these fancy % arguments, and we return some value that's an I64. This is not Julia code. This is what's called LLVM intermediate representation. You don't need to know this, and I encourage you not to learn it, but I think that it's nice to know that it exists and that there's depth here, that you can understand what is happening. So here you can see that we're adding two integers together when we call 1 + 2. Within that same plus function, though, if I were to pass floating point numbers, right, instead, the generated code changes. Now we're not adding I64s or 64-bit integers. Now we're F adding or floating point adding doubles, double precision numbers. And so you can kind of get a sense, this is what's called specializations, where you can have a single function without any type annotations. And as you pass it new argument types, Julia will specialize it down to the exact machine arithmetic intrinsics that are the fastest that you can have. So this applies to all the functions that we write, including things like find closest to here, right? So I can ask for what is the code LLVM of my find closest to for, say, float 32s, right? So here I'm just going to have a simple 3-element float 32 and pass in a float 32 data point. Well, then I generate float 32 instructions that are, you know, made for that. And so you can kind of see that happen where, you know, instead of double precision, we're loading single precision values and doing single precision floating point values. The same thing happens if I were to use integers. So if if I did just simply an array of integers, 2, 3, 4, and I asked, you know, for the integer 3 here, right? So if I just do integers, well, then I'm going to use integer arithmetic instead of floating point arithmetic. And you can, again, go through here. This is, you know, lots of gibberish. The key thing is that these instructions have changed based upon the arguments that I passed in. And so this is at the core of Julia's performance really is this just barely ahead of time compilation based upon the arguments you pass will generate specialized code, even though we never talked about types in our function itself. So to get good performance, you don't need to talk about types. I think I might stop there in interest of time. This took a little bit longer than I expected for the serial performance, and I really want to get into parallel performance. The last section here is just kind of a fun table talking about memory latencies and how our processors are so fast that it's hard for us to reason about, right? I've been seeing times ranging from nanoseconds to microseconds to milliseconds. And what are those things? And it's hard to even wrap your head around how fast a nanosecond is. That's what generally about one processor instruction can be accomplished in about a nanosecond. And it's kind of cool to think about nanoseconds in terms of speeds of light, because that's what our limit, right? Our speed limit in our computers is the speed of light. And well, a nanosecond is about a foot. So you can go about 11 inches, or the speed of light goes about 11 inches in a nanosecond, which means that you can add numbers in your computer faster than you can possibly move data from one side of your computer to the other, which is kind of cool, right? It's pretty wild. But it's hard to represent and hard to understand. So this table here kind of takes what we know of our CPU cycles and scales it to a human scale where a single processor instruction happens on the order of 1 second instead, and scales these things up to the time that it would take for me or you to do a very simple integer arithmetic of 2 single or double digit numbers, say. And so we have our CPU cycles here at this level. Our main memory exists farther away, right, which takes time to get there, based both speed of light, negotiating all the circuitry and everything. In fact, it takes about 4 minutes to gather data from scratch from your main memory. And so if every time you wanted to add 2 numbers together, you needed to wait 4 minutes, that would be pretty significant bottleneck, right? And so you don't want to do that. So our machines, modern machines, do what's called aggressive caching of these memory, of this memory, to move it closer to your processor. And so level 1 caches are the closest to your processor. Level 2, level 3, each move them closer. You can kind of think of it as, the 1 second is doing the addition. 2 seconds would be looking up an addition that you literally just did, right? That's on the same piece of paper that you're working on by hand. 7 seconds would be maybe on the previous page. You have to reference it a little bit farther away. 1 minute might be in a drawer on your desk. And then the 4 minute is inside my filing cabinet in the back of my office, where I need to go over there, rifle around, find it. It takes me a while to find. So this is kind of a nice way of thinking about how memory latencies become important in performance, and particularly parallel performance, where we're not just talking about single memory access, but might be hitting, say, a solid state disk, which is excruciatingly slow in this time scale, right? It's only 50 to 150 microseconds in our real world times, but in the perspective of your processor, that's like on the order of days, right? It's so slow to hit a solid state drive. And these are the fast drives that we've all been transitioning to, because rotational disks, old spinning rust disks, take months to do. Or if you have to hit the internet, heaven forbid, it's going to take years in order to get the 2 numbers that you want to add together. It'll just take you 1 second to add together, but you need to wait 11 years to get those 2 numbers. And so this is where we'll talk some about data movement costs as we go forward, and how to optimize for these, and some of the effects that caches give us, and headaches that caches give us when we talk about parallel performance. But that should put us in good stead for our parallel compute. I'm sorry, I went about 20 minutes over here. I think this is hopefully a good refresher of Julia syntax. I can take any questions that you all have on Julia syntaxes or how they work. Vish asks a good one about, when we started with this, we have all these dots here in our first find closest implementation. And what do they do and how do they work? Well, it's perhaps most obvious to see what's going on here if I tried to do this without the dots. And so I have my data here. Let's go back to my terminal here and say I have a point of 0.5. And if I tried to do data minus 0.5, I'll get an error that says, hey, I don't know how to subtract a single number from an array of numbers. What I do know how to do, so this is a no method matching error. It's saying there's no subtraction method that will apply to arrays and a floating point number. Hopefully Julia says, hey, I do know how to do element-wise subtraction, however, and for that we use our element-wise syntax of dot minus. And so by dot subtracting, then we get our data offset by this point and subtract this all out. In the same way, if I were to try abs of this without a dot, it's going to say, hey, I don't know how to take the absolute value of an array as a whole. Now, we don't have that helpful error message here, unfortunately, at least not yet, because this isn't quite as common, but the same principle applies in that I want to apply this point-wise across my entire element. So if you're coming from, say, NumPy or MATLAB, by default, all of those operations are broadcasted, right? Because they end up hitting some function implemented in C to give you the good performance that you would expect. The downside is that, doing the naive thing, you end up with an intermediate that has all the data offset by 0.5. You have all the absolute values, and you end up with lots of intermediates. Julia is able to see, hey, all of these are dots here. That means they're all happening element-wise across this one data set. It can introspect that and do what's called broadcasting in a fused loop that just takes one pass over our data set and does it efficiently that way. So yeah, that's broadcasting in a nutshell. Any other questions on any of the things we talked about? This is setting the groundwork and setting the stage for a lot more complicated things that we'll be talking about. So if you have any other questions, now's a great time to ask them. If not, let's take our next 10-minute break. I'll reset my timer here and kick it off, and we'll come back at about 1/2 the hour. Sorry that this one went a little bit over, but see you around 1/2. Okay, welcome back, everyone. Let's dive into our next lecture here that will talk about starting to make use of parallelism and getting parallel performance out of our computers. So the first form of parallelism that we're going to talk about is a form of parallelism that can happen automatically, which is the best sort of parallelism there is, the kind of parallelism that you as a programmer don't need to worry about at all. So this is what's called SIMD, which stands for Single Instruction Multiple Data. And we'll be looking at Notebook 30 here to look into this. So the basic idea here, and sorry, I still need to figure out how to display LaTeX code nicely in VS Code here. It's the one thing that we're missing in our new architecture of running these courses in VS Code. You end up seeing raw LaTeX, which doesn't look very nicely. But the basic concept here is that instead of saying x sub 1 plus y sub 1, doing this addition, and then x sub 2 plus y sub 2, and so on and so forth, right? I don't have these things defined, but you get the idea, right? Instead of doing 4 independent additions for 4 different data points as you're adding 2 vectors together, modern processors have vector processing units that can do 4 additions at the same time. This is what's called SIMD, right? It's taking one instruction, that is the plus instruction, and instead of evaluating 4 pluses for our x sub 1s, x sub 2s, x sub 3s, x sub 4s, and y sub 1, y sub 2, y sub 3, y sub 4, it just does 1 plus between 2 vectors, 2 small vectors. So that is, you can think of it, I should change how I do this. I should say, sorry, you have x sub 1, x sub 2 plus y sub 2. You have x sub 3 plus y sub 3, right? And x sub 4 plus y sub 4, right? So you could do 4 separate additions. That's 4 separate instructions like this that take all of these together, right? And do this. And why don't I just copy this? I'm going to change the way that I have this written. Right, so instead of doing these 4 additions separately, where you have these 4 things separately, what you can do is you essentially do the same thing, but you group them into vectors, right? So that would be, let's take the same setup, but instead these are all grouped into a single column vector here, right? And you use a single plus function that can apply to this entire column vector that's built like this, right? Where you have these things bundled into a single vector, and you just do a single plus that applies across the entire vectors of these 4 things. And kind of the magic here is that this vector addition between our 4 element vectors here, kind of my crappy ASCII art, this single plus with 4 multiple data points takes exactly the same time as our scalar plus function does here. So this vector addition takes exactly the same amount of time as a scalar addition, which is pretty wild. Doesn't necessarily have to be that way, but it happens to be the way that these units are implemented. And it's really nice for us as programmers to think about them, right? Because it means that, well, by magic, if we can structure our code such that our computer can use the same instruction across multiple data, then we should be able to get a nice 4x parallelism out of a single core. So that's the way it works. so how can we make this happen? How can we see this? How can we know what's happening? Well, let's create a simple function that can play with this and understand what's going to go on here. So let's create a vector of 100,000 elements, just kind of like what we did before with 5,000. Now let's use a slightly bigger vector to give us a beefier problem, or we can see more performance. And what are we going to do? Well, let's just compute the sum of it, right? Well, of course, I can write in Julia sum of A and get the sum of these 100,000 elements pretty easily. The answer is going to be around 50,000. They're uniformly distributed between 0 and 1. That makes sense. Great. I can use this built-in Julia sum function, right? And that's fine. It happens to be implemented in Julia, and it's nice and performant. But I can also just define this myself. And remember, in Julia, for loops are fast. So we can just write a for loop that will do this for us. And we can do it, again, without thinking too much about types, right? I don't need to say even that this is an array. I just define a function, send all these lines to my REPL, and define this simple sum function here. What it's going to do is it's going to create a bucket, and I'll call this my result, that is going to start with a value that's 0 of the element type of A. So this was how we can make sure that we're type stable, right? Because we want to make sure that we're using the proper arithmetic. And so I could have said, let's start at the integer 0. But then if I passed in a floating point number, this would need to promote to evaluate to floating point numbers. It wouldn't give me quite as good performance. So this is kind of a nice generic way of starting at a 0 element that we can add to and then iterate over all the indices in A and index into it and add into our bucket. And there's an extra macro here that I'm using for performance reasons, this inbounds macro that says, hey, let's disable bounds checking here. We know that we're iterating over each index of A, which VS Code helpfully says when I hover over this, which means that we know that all of these indices are going to be inbounds, right? We can tell Julia, hey, don't bother checking bounds here. Let's skip that bounds check. And that can, again, give me extra performance because it's less time spent doing a safety check and more time spent doing the operation that I want, which is taking elements out of A and adding them into my bucket. So I can run this and just see what is the simple sum of A. We get an answer, again, around 50,000. That's awesome. Interestingly, it's a little bit different than what I got for my sum, and we'll talk about why that is. The last bits here, the last 2 digits, are different, which is kind of interesting and is important, and we'll see as we come down. But again, let's pull in our benchmark tools package and just see how long this function takes. And we can see, again, we're going to flag the argument as an argument, so that way we can specialize on the element type, like what we want to do, as we learned in the last lecture. And we can see that it takes about 100 microseconds. So is that good? Well, we can, again, compare it to our built-in sum function, which hopefully Julia is doing the fastest thing possible there, or doing the best thing possible, maybe. And you can see that, holy cow, it's 8 times faster. Almost exactly 8 times faster, in fact, on my computer. The performance that you see will be different on your computer, but I'd wager that many of you are going to see numbers that are either 4 times, 8 times, or even 16 times faster than what it takes for the simple sum here. Which is interesting, right? So 100 divided by 12.6 is almost exactly 8. 8 is an interesting number here, right? That's a nice power of 2 and might imply that maybe Julia is by default using some form of 8-fold parallelism here. And of course, as you'd expect, given the title here, indeed, that's exactly what's happening. We're using single instruction, multiple data to get 8-fold parallelism out of our our performance built in. But it didn't happen when I wrote my simple sum function, which is interesting, and we'll see why that is in just a second. We can also play an interesting game here, right? So remember that when we ask for, when we have our A, which is a 100,000 element long random vector with uniformly between 0 and 1, we get float 64s, right? Our type of A is an array of float 64s. That means that each floating point number has 64 bits of precision. Translate that to decimal, it's about 15 decimal digits of precision. And that takes up 64 bits, or about 8 bytes, exactly 8 bytes, not about 8 bytes, exactly 8 bytes. And so that's how big our array is, right? It's going to be 800,000 bytes long, because we have 100,000 elements, each of which are 8 bytes. So we have 800,000 bytes, or 800 kilobytes, right? So we can play a fun little game by, instead of asking for 100,000 float 64 elements, we can explicitly say, hey, let's get float 32 elements. So these are going to be 32-bit precision, or about 7 decimal digits precision. They only take 4 bytes of memory each, which means that we can fit 200,000 of them in the same memory, the same length of memory, as we can fit 100,000 float 64s. So let's have this A32 vector, which is our 32-bit vector that it's taking up the same total amount of bytes in memory, but we have twice as many elements. And now you can see something that's kind of fun. So remember, it took me about 100, 100 microseconds, 100 milliseconds to do the sum of our 64-bit. It took exactly twice as long to take the sum of twice as many elements. That makes sense, right? We have our simple sum, we're iterating over each element, we add twice as many elements, it'll take twice as long to do that, even if they're 32-bit or 64-bit, it's the same performance of doing that. But let's see what our built-in sum function does. And if we ask for our built-in sum function for this 32-bit floating point number, we get about the same performance as we saw before. Which is kind of crazy, right? Now we're not 8 times faster than our naive implementation of a sum function. We're actually 16 times faster. Again, hopefully that's throwing up some flags in your mind about why this might be. But it's pretty cool that the timing between sum of A, which is our 64-bit values of 100,000 of them, and the timing of the 32-bit values is about the same. It's not taking twice as long at all. So our built-in sum function is indeed doing something really cool, really interesting with parallelism here. And the answer comes down to how SIMD works. So let's just try using SIMD ourselves. And I guess, well, yeah, let's talk a little bit about why this is. So the basics of how our architecture works is that, the processors have a set width, bit width of SIMD width of how many bits can it process at once. And for those of you who are familiar with processor terminology, this is, the general term is SIMD, single instruction, multiple data. And the exact implementations that you might have seen have continued to grow in the number of bits that they can process at once. And this is how kind of Intel has marketed this in all sorts of crazy ways. That when it was first introduced, it was called SSE, or some sort of vector instruction set, and on and on. And so the most recent version of this is called AVX 512, and the 512 there. Well, hopefully it gives you a flag again. Maybe it's 512 bits wide. And if it's 512 bits wide, that means that it could process, 64 bytes at a time, which means that it could process 8 floating point numbers at a time, right? That's kind of how this could work and how it could get going. So this is the basics of SIMD. And the cool thing is that when you shrink your data element size, so if we go from an 8-byte element to a 4-byte element, well, then you can double the throughput through your SIMD execution. You can apply that single instruction to more data, to even more multiple data. And so that's what's happening. That's the even multiple number performance and how it's going. So let's do this ourselves. And the magic here to get this going is just a special flag that says, hey, let's enable SIMD. Let's annotate this for loop. Let's add a macro special performance annotation that says, let's evaluate this in a manner that is happy to use SIMD. And now our naive thing, our very simple, 6 lines of code here, whatever it is going to rival the performance of our built-in function of 12 microseconds, about 8 times faster than our naive performance, and gives us the same performance regardless of our number of elements. It's just based upon the bit width here, right? So we get exactly the same performance as we did before. So why did we need this magic macro to enable this? And why doesn't Julia just automatically do this for us every time that we use a for loop? Why can't it do this? Well, the answer there comes from the difference in values here, right? So if I look at the 3 values that I get back from these 3 functions, right? So our first naive implementation, our explicit SIMD implementation, and the built-in implementation, all 3 of these are giving me slightly different answers in the last few bits. So if you look at the last few bits here, we get 76,368, 76,314, 76,315. So each one of these implementations is giving me a slightly different answer, which is kind of crazy. Like, how are there different answers when I'm adding together a bunch of numbers? Like, how could there be multiple answers? How could Julia be getting this wrong? And the answer is that it's not really getting it wrong. It's just that floating point numbers have a limited precision, right? And so if I am adding them all in, you can think of it as, a bunch of scientific notation numbers. So, if I have a bunch of scientific notation numbers that I'm adding together with only, say 4 decimal digits here, right? 1.234, 5. Some other set numbers, I'm adding all of these numbers together and putting them all into the same accumulator. Well, as I add them, I'm going to start adding these things together. So, I can do this as a function, add them all together here, kind of like as you would in elementary school, right? You can add them all together. But if at each point that I do this, I need to round to 3 decimal digits, right? Then after I do some of these additions here, I'm going to round again to 3 decimal digits and I get 12.8 maybe. I've rounded, and then I add another number in here. And if I just keep adding into the same bucket, this bucket will get very large and I'll start losing the bits off the right-hand side as I round and as I do this intermediate result. And so adding things incrementally, so the way we first did it here with our for loop, where we just go from left to right across our array, we're saying that we must add this into our result bucket incrementally, just marching down our array, adding it, and Julia will follow that those marching orders perfectly. And this is important in getting the exact result that you want, right? This is doing exactly what I said. It just turns out that this isn't going to be the highest precision way of getting my floating point number, because we're going to get rounding errors or rounding approximations, I should say, as this result gets bigger, we're going to start losing those last bits of our elements in our data set. And so that's why we do this. So when I've done this in a SIMD fashion, it's allowing Julia to rearrange our results. So we're no longer just adding it into a single bucket. Essentially, what's happening is that behind the scenes, Julia is rewriting this to be a for loop that will go from for I in, say 1 by 8. Well, let's just do 4 to make this simple, to, length of A like this, right? And we're having 4 different results. Result of 1, is, plus equals A of I. Result of 2 plus equals A of I plus 1, and so on and so forth, right? You have all of these 4 result values that, this is the result sub 3 and result sub 4, and this is I plus 2, I plus 3. And so we've rearranged our algorithm essentially by writing this SIMD. We're effectively saying, hey, let's just have one for loop that does this. And because we have this 4 element vectorization here, well, we can have, instead of one single bucket, let's have 4 buckets and then return result 1 plus result sub 2, and so on and so forth, and add all of these at the end. So we have 4 buckets that we're using simultaneously that we're adding together, and giving us, this is effectively the algorithm that Julia is doing for us behind the scenes when we add this @SIMD annotation. And the @SIMD is important because it allows you to do this kind of restructuring, right? We get a different answer. And so Julia won't do that automatically for us because of floating point is just annoying in this manner. It won't automatically do this for us. And so the SIMD macro is often needed when you're dealing with floating point values. And it'll do this kind of restructuring. And importantly, all 4 of these plus operations here, right? These 4 plus operations, they all are happening in one go, right? That's part of the vector unit, and it's doing this vector plus this vector in a single go, and that's how it can do it. And the cool thing is, because we don't worry about element sizes, right? If our element size is appropriate, it might do an 8 length here, or it might do a 2 length here, or something like that, and automatically give me the correct number of buckets without me needing to do this restructuring myself and give me the vector addition the way that I want it to go. So that is SIMD and the way that works. It's pretty straightforward, and that's why it doesn't automatically do it, right? And so that's what this text is talking about in the next block, is how we can allow rearrangement of floating point additions. And that's really the biggest reason you do this. And in fact, if I were to do this with integers instead, so I have a vector of B here that is, int 64 is just a bunch of single digit values of, 100,000 int 64s. Well, then my simple sum that just does the simple naive left to right thing without any SIMD annotations, that gives me the exact same performance and the exact same number, because integers don't have this annoying behavior of round off, right? Then I get the exact same performance as my sum and the exact same value. And importantly, you can actually see that this happens by doing the same 32-bit thing. So by default, if you're on a 64-bit system, this B will be 64 bits. I can do the same sort of game with 32-bit numbers, and you can see that you'll get the same sort of performance, right? We're automatically SIMDing it, which means that doubling the number of elements doesn't change our runtime performance, because we're at the same time having the number of bits, which fits through that SIMD lane just as well as everything else. So this game of having the element size and doubling the length is kind of a fun way of introspecting your algorithms, but it really only works in contrived situations, right? And so there's limited situations where you can see how that works. How can we tell if something is getting vectorized? Well, here's where I'll lean on those intermediate results that we talked about in the last lecture about how you can look at what's happening. I'm going to turn off debug info here just by saying this, adding this special debug info equals none flag, just to make the output of LLVM a little bit more concise. This will, if you have debug info, and it'll just show the line numbers, which I'm not interested in this particular example. What I'm interested in seeing is how does this, lower level representation show me that it's getting vectorized or not. And so you can see how Julia is talking to our computers in ways of multiples that we get here, right? And so you can see with our SimSum A32s, we end up with this 8x performance, right? You end up with an 8x performance increase, and you can see that exactly here by the vector additions that are happening, right? You can kind of scroll through here, squint a little bit, and you don't even need to really understand where in the algorithm we are here, but you just see the algorithm literally littered by all of these 8x floats. And this means that all of these operations, like here are a bunch of addition operations, all of these operations are happening eightfold time with eightfold parallelism on a single core. This isn't multi-threading. This isn't doing anything special. This is just using the instruction set of our processor to our advantage and expressing things in a way that we can use single instruction multiple data here. And so this is how you can see that it's getting vectorized. And you can see, if I change this to our 64-bit values, well, then we get 4x doubles instead of 8x floats. Or if I use my integer values, right, B32s, well, then I get 8x int 32s. Or B, which is 64 bytes, well, then I get 4x I64s. And again, you do the multiplication, you can see exactly 4 times 64 bits. My computer has a 256-bit width SIMD unit. So that's how you can get these sorts of performance things. The challenges in using SIMD, well, the biggest challenge is convincing Julia and its compiler framework that it's allowed to use SIMD, right? There's a lot of things, restrictions here, because it is a core instruction. It really only applies to core arithmetic, right? The core things that you're doing, like addition, multiplication, the kinds of things that your functions can do. So you can look at the documentation here and see all of the little caveats and things like that. It really only works if it's the innermost loop. So if you have nested for loops, adding SIMD outside won't change things. The nice thing about the @SIMD macro is that if it fails to happen, well, then it's just not going to happen, right? You just won't see the performance. You're not going to see race conditions. You're not going to see problems. It just won't give you the performance you were hoping for. So there's a slightly trickier case here that we can talk about briefly. I think might be helpful just to kind of see. Yeah, sure. Let's talk about this. Mike is asking a good question that's been rattling around in my head as I've been talking about this. He's very astutely saw this, So I have a 256-bit width SIMD unit in my processor. Why did I get 8-fold speed up here? And to be frank, I'm a little puzzled by it myself. I think right, because I should only see 4x performance, not 8x performance by splitting my thing up this way. And I think it's because each single core actually has 2 SIMD units in it. Yeah, I think it might be the loop unrolling here. So let's look at the int64 values here. So so in my loop, you can go in here and see exactly what's happening. The other canary in the coal mine here that can tell you, hey, this is running a loop, a vector loop, is that there's a vector.body section here. And so it is actually unrolling my loop here and doing in each loop. So this is my loop section here of, getting out a bunch of values from my vector and getting them all out. This is, getting a bunch of values out. And then it's doing 4x additions in each loop. And so this is, it is unrolling my loop. So that way each iteration of my loop, I'm doing 4x additions. That doesn't explain the whole thing though. And I think that the answer, I can go one level deeper here. Let's just see. This is a little bit interesting. So code native is the exact, this is the assembly then. And it's a little bit harder to read. And yeah, so it's doing 128. So yeah, I actually have 2 SIMD units available to my processor here. They use two different sets of registers. So there's the YMM set of registers and the XMM set of registers. And I think the reason that I'm getting 8x performance here is a latency thing where these sets of instructions and these sets of instructions, while they happen sequentially, or you can think of them happening sequentially, there's a latency between these two. And because I can load up these 2 separate sets of SIMD units, the YMM and the XMM registers simultaneously, then I only pay for the latency of this instruction once. And then the core overhead is the latency of the instruction and not the running of the instruction. It's a little bit inside baseball here on processor performance and the exact registers that we're using. But I think that's the magic that's going on. This is an AVX2 system. I know that the Mac laptops don't yet have AVX 512 and most laptops in general don't have AVX 512. And so I do know that I only have 256 bit width SIMD units in my laptop. It's just that I can use 2 sets of registers at the same time and kind of decrease register contention. It's a little bit advanced or very advanced hardware deep dive. But the cool thing about Julia is you can ask those questions. And I'll double check with our compiler team during our next break just to see what's going on there. But I think that's what's happening. All right, so that's SIMD. There's this trickier case of doing an in-place diff algorithm, which is kind of a nice case of something that's slightly more more complicated than your simple addition example. And this is a good example where Julia itself has a diff function, right? So I can take the diff of my B, that's just the sequential differences of all of these elements, right? My B is a bunch of, numbers from 0 through 10, and I can just go through the sequential differences and I end up with, one less element. So the difference between 8 to 2 is -6, from 2 to 6 is 4, and so on and so forth, right? That's the diff algorithm. Of course, doing this allocates a brand new array. And one of the ways that, if this were a core part of my algorithm, I might want to reduce some of the scratch work that I'm using. And one way to do that would be an in-place operation. But Julia doesn't have an in-place diff bang function. That would be the convention of how you would spell a diff algorithm that would do this. So we can define that, right? And again, it's very simple. You just have a output values and your input, and you just want to start with your input and iterate over them all and return your values. And that's, you just incrementally do it. The only tricky part is you need to define where you start, right? Instead of having one less element, maybe you would have the same length of elements, but we can define this, start up with A and B, and, we can go in here, compute the diff of B into the A pre-allocated vector, and it'll give me better performance. And I can say, hey, is that the same? Sure enough, it is. And of course, I can time this, right? And I can see, hey, is my in-place algorithm faster than my out-of-place algorithm? And sure enough, do this diff bang, and you can see it gives me 14.6 microseconds to do it in place with, importantly, no allocations. And the diff algorithm is about twice as slow because it needs to allocate its result and move them. And so by pre-allocating my result, I can improve my performance. And so that is that's the way we can do this and get really nice performance here, right? I've got this this structure that's nice and easy to do, and it does it into a new vector, right? I'm taking I have two separate vectors that I'm passing in here, an output vector and an input vector, and I can work my way through my algorithm and store my results in my output vector. Now, interestingly, what happens if I try to do this in place, right? So I could make a copy of B and do diff bang into my, time this, I'm sorry. So I can take my B copy and do the diff bang of it into itself, right? I can just incrementally update, work my way through my vector and incrementally update my vector with its results. And suddenly I will get an answer. I'll get the same answer. Julia will do the right thing, but it's going to be catastrophically slow to do this in place, which is puzzling and interesting. And again, you can kind of see by the timings here. So remember, our diff bang function takes about 14 or 15 microseconds to do. Doing it and trying to do it in place, I end up with 225. Well, 225 divided by 15, that's almost 16-fold difference. And that's almost exactly, the SIMD width that we were talking about, right? The 16-fold speed up that you can see with SIMD. So suddenly when I try to do this in place, I can no longer use SIMD. And I'm not using SIMD instructions here, right? I'm not explicitly saying SIMD here. Julia is automatically doing that for me in one case, but when A and B are the same vector, suddenly it fails. And that's because, well, think about what's happening, right? I'm updating A in place, and these are suddenly all the same vector, right? A equals A, they're all the same vector. I'm passing in the same vector in these two arguments. So we're updating this in place. So that means that I can no longer unroll this into a 4x update because I'm using my previous answer here in my result. And so suddenly, if I were to do this SIMD, it would give me the wrong answer, which is kind of fun to think through. I encourage you to think through why this is the case. And there's a fun little exercise. you can actually rearrange your algorithm here. So that way it's SIMD safe even with the same input and output vectors, which is kind of a cool little exercise to do. It just kind of takes a little bit of thinking around, about how you're accessing your values in a way that you don't need to depend upon the previous result. In this example, we are depending upon the previous result because I'm accessing the previous index here and storing that into this one. But it's a pretty simple shift to not do that anymore and allow this to be SIMDable. So that's kind of a fun game. So that's what's happening there. And you're going to see this happen in our LLVM code, just like before. Again, let me turn off my debug info. Sorry, I should have done this in my in the actual notebook. Just removes a little bit of gibberish. But you can see, so it looks like this should be SIMDable, right? There's my 8x floats all working nicely for me here. But what's happening is Julia's doing a memory check to see, is this safe to vectorize or not? And so before we get into our vector body here, before we get into our vectorized loop, it's doing what's called a memory check. And if our arrays conflict in a way that, iteratively doing this would give me a different answer, we'll go to a scalar loop. Otherwise, we'll go to a vector loop. So Julia is actually compiling for us 2 different loops into the same specialized function, one that can be vectorized if it's safe to do, one that can be scalar if it's not, and it'll automatically use the correct one to give me the correct answer. And so here's my vector loop. And somewhere in here is my I guess this would probably be my scalar loop. And you can dig into this, see how this all works. It's kind of fun to see. But that's a little bit. If you really want to get your hands dirty on SIMD, there's actually a SIMD.jl package that you can manually do these things and do all the nitty gritty stuff. But really, I encourage you to just lean on what Julia does, know some of these tips and tricks to know when you're generating vectorized code. And it can be a huge multiplier to parallel programming, right? Where you want to move towards parallel programming and you'll want to get these things together. So that is how we'll move forward. And prefixing a 16-fold speed up is just a 16x multiplier that you can then multiply against multi-threading, that you can multiply against distributed compute, that you can multiply against all sorts of things. And so adding a 16x multiplier is never something you should turn away. And making sure that you're using those SIMD instructions is how you make the most out of your processor. So that is SIMD in a nutshell. This is built-in parallelism that is, at the core of your algorithm that you want to use. And so you need to do all the performance best practices in order for these things to happen. And there's some tips and tricks here, but you can get huge speed ups that allow you to do this. Newer processors have that, what we were talking about before, the 512-bit width lanes. They're a little bit tricky. They are generally on server chips, and they're so power hungry that they can actually end up slowing down some code because you can end up, hitting your temperature ceiling on your processors, which is a little bit unfortunate. But in general, you'll see a nice big speed up for free using SIMD. There's a question from Andre that I breezed past there. Just a recap on why is it, so remember we have this simple sum function. Why is it that when we use integers, does simple sum give me the same performance as my built-in sum? And the answer is because Julia is automatically able to do the vectorized rearrangement that we talked about with integers, because integers aren't order dependent, right? And so the key here is, let me go back to, did I delete that? I hope I didn't delete that. Yeah, good, here. This is the key algorithm here, right? Remember, when I'm using floating point numbers, I need to explicitly use this at SIMD to say, hey, you can rearrange the order of operations in this for loop. And that's a quirk of floating point numbers, that the order of operations is significant. When I'm using integers, doesn't matter, integer arithmetic is associative, it's commutative, your computer does it, as you would expect it to. And so it can automatically do this rearrangement behind the scenes without changing the result. And so that means that Julia will do that for you automatically. The only reason I needed the explicit SIMD here in order to get it to work is because we were using floating point numbers in my first example. That's a really good question, and a nice little recap of, the goal of SIMD is for it to happen automatically. And there's just a few cases where you need to be aware of with, floating point numbers are really the most common one that you need to express explicitly. Hey, I don't care the order of operations here. Feel free to rearrange them. And the cool thing is that by using 4 buckets, we actually get better precision, right? Because now each of these 4 buckets isn't going to get to be quite as large of a quantity. And so you end up dropping fewer bits off the last end of each element because each of these result buckets is about as quarter as big. And Julia's sum gives you a different answer because it tries to do the same sort of structure, but in a more general way, and tries to exploit SIMD at the same time. And so that's why, the SIMD sum is a little bit faster, in fact, than Julia's built-in sum. You'll see that this is using the SIMD architecture as fast as possible, whereas the built-in sum will be a little bit slower, but give us slightly better precision. And so you can see that happening here, where we get a slightly different answer, but better precision. And we lose a little bit of speed, but we're still using SIMD and getting it. It's just arranged slightly differently to try to preserve as much precision in our numbers as possible. And so there's a small trade-off that Julia's built-in sum function is doing there that is trying to preserve as many bits as possible of precision. With that, let's take our last break, and then we'll talk about some real parallelism in the form of multi-threading when we get back. Maybe, are folks okay with just a 5-minute break, since we're running a little bit over time here and we only have about 40 minutes left in our course? I'd prefer to give ourselves time to work with multi-threading, and we can come back to multi-threading tomorrow too. But let's do that. Before I take a break, I want to ask you all to do one thing to set us up for our time tomorrow. We're going to try something new, something fancy that we've not tried before, that'll help us do some cool things with parallel programming that you can't do on your laptops, and that's using Julia Hub. And so if you can, go to juliahub.com. I'll copy and paste this into our chat box here. So during our break, head over to juliahub.com, log in, and log in with any one of these open authentication mechanisms, and then send me either privately over chat. Yeah, I guess privately over chat would be the best thing. So if you just change the to box on your chat button to be to me directly, and send me the email address that's associated with whatever account you used to do this. So you can log in with GitHub, whatever email address is associated with GitHub. We'll then flag your accounts for some free compute on Julia Hubs for tomorrow's course, so that way you all can test out some larger scale distributed and GPU compute. It's going to be a new try thing. So Julia Hub is a new thing that we're doing, and this is going to be the first time that we're trying it. So maybe in the next hour or so, I'll remind you at the end of the course to give me your email address that you're using to log in to Julia Hub, and we'll enable some compute for you tomorrow. All right, so let me pull up my 5-minute timer after that little instruction, and we will see you all back here like 26 past the hour. All right, welcome back for our last and final session in this day's session. We're finally actually going to talk about multi-threading, some of the core basics of real parallelism here, where we'll go into Notebook 40 on multi-threading. So everything that we've done up until now is just using a single core. We were still able to get some parallelism based on SIMD, but now we can take that and parallelism that we got and multiply it by the number of processors or cores that you have. And well, the first challenge is knowing how many processors you have, and it's tricky because it's complicated. So you can ask Julia for version info that prints out a bunch of stuff about Julia itself. So I happen to be on an old 1.5.0 version of Julia here on Mac, and it tells me a little bit about my processor. And it says that I have 12 processors, all running at 2.6 gigahertz, some usage information, how much memory I have, all of these things here. So it's saying here that I have 12 processors, right? So what, processor number 1 through processor number 12 all have the same speed of 2.6 gigahertz, which is interesting. And actually, since I'm on a Mac and in a GUI, I can go in here and ask, hey, what about this Mac? Which, goodness, that's small. Let's see. I don't know if this zoom in works here. You can see a little bit here and see a little bit more details. So processor 2.6 gigahertz, but that doesn't tell me how many cores I have there. There's a little bit more, but it's not telling me how many cores I have, right? And I can go in here and get more information from a system report, and go in here and let's see, can I make this bigger? I guess not really, dang. Yeah, so you can go in here and get some more information. So here, it's a MacBook Pro, a little bit more information. Here's some information about those caches that I was talking about. That's kind of cool. Aha, and here, 6 cores, which is interesting because Julia said that I had 12, right? And so why does this say 6 cores when Julia was telling me that I had 12 processors? And in fact, if I go into Activity Monitor, which is one of the ways that you can pull up information about Julia or about your processor, you can pull up a processor load history thing, and it shows all the things that are running on my computer, and it gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 processor bars here. So it's kind of sort of saying, it's giving me 12 different processors that are showing me the load on 12 different things, but I only have 6 cores. What's happening here? And the answer is what's called hyperthreading, and it's at the core of throwing more transistors at single core performance, right? We've talked about how we kept getting more and more transistors, trying to improve single core performance, and effectively what ended up happening is our individual cores got so big, so beefy, so many transistors on a single execution unit that it became efficient to rapidly swap between 2 different tasks. And that's what's called a hyperthread, where you can have 2 things happening on a single core at a single time, and it is exposed to the operating system like there are 2 separate cores here. So you have your physical core and a hyperthread. And my operating system is doing the smart thing here of trying to schedule as much as possible on the physical cores. And you can see every other core that's listed here is actually seeing, some usage and in recording my voice, sending it to y'all, running Julia, all those things. And the hyperthreads are relatively empty, right? There's not much happening on those. But if I were to stress my system, it would start using those as well. And it just allows the operating system to rapidly swap between 2 tasks where you can have multiple things going on at the same time. Now, turns out that this ended up being a security vulnerability, and that's what, so if you're in a cloud platform or something like that, you'll actually see these hypercores being disabled completely because you can end up finding some information about other processes that happen to be residing on the same core as yours. On a local desktop or a consumer desktop, it's not as big a deal because hopefully I should know all the things that are running on my computer, and I should be able to trust all the things that are running on my computer and not to spy on other tasks. But it is a security issue, as it turns out. But this is how our processors work. And so the key thing is that, the hyperthreads aren't true computation cores. They're not truly going to have all of the hardware that's available to it. And so generally, if you're doing big numeric routines, well, you only want to use, on my machine, you would only want to use 6 threads. If you're doing, on the other hand, something in which you are doing lots of task switching, so like running UIs, waiting for inputs, things like that, lots of switches between different applications, well, then it makes sense to use your hyperthreads because then you're waiting on user input, you're not exploiting, you're essentially shortening the time that it takes to switch between tasks using hyperthreading. So that's hyperthreads in a nutshell. There's a little bit more information on how that works in here. And we can ask, there's a Julia package called hwloc that will tell you the number of physical cores as well. So that's kind of the key thing that you want to key off of. And there's work going on to bring some of this identification, system identification, into Julia itself, and to hopefully eventually start Julia up with the appropriate number of threads automatically. So that's what's happening in our modern hardware. We would want to start Julia with 6 threads of computation in order to do this. So that's the first point on multi-threading, is just simply knowing what your hardware exposes. This number will be different for all of you depending upon what machines you're using. Then, you can actually see that Julia is using multi-threading by default. So if I, bring in benchmark tools again and do, for example, a matrix multiplication, this is by default using all my cores. So if I go back to my, my processor, utilization graph here and keep it up on the side and run this A star matrix multiplication between 2 matrices, you can actually see it hitting all of my cores here. All of my cores have had activity when I did that. And you can see that spike in my processor utilization graph here, where I did that. And in fact, it even bled over into my hyperthreads because my operating system started using the hyperthreads because there was lots of core numerics going on. And so this is by default multi-threaded. Matrix multiplications, linear algebra operations by default use multi-threading to do their operations. And you can turn that off in the linear algebra package just by asking BLAS, which is the linear algebra subsystem that we use to change the number of threads that it uses by default. So you can set this to be, say, for example, 1 thread, benchmark it again, and this time you'll only see activity on 1 core instead of all 6 of my cores in my utilization graph here as I'm going about it. It's a little bit muddled with all the other things that are going on my computer at the same time. So it's not as obvious. What is obvious though is the timing, right? So 44 milliseconds here in the single threaded case versus by default, it took 11 milliseconds. And so you can see that it is giving me a nice 4-fold speed up there. Why not 6-fold? Well, that might just be because due to the structure of my matrix multiplication, I'm only doing 1,000 by 1,000. It might have been that my linear algebra library decided to split my array into 4 parts instead of 6 and could do it that way instead. I don't, it kind of depends on the size of your matrix and such, but you'll see a nice multi-threading speed up here. So that's the end of our notebook, right? Julia's multi-threaded. You don't need to do anything. We're done here, right? Well, no, of course not. The whole point of this entire lecture and this entire thing is, you know, how can you do this yourself? How can you get your own multi-threaded algorithms up and running? So that, and that's kind of the magic of Julia, is that you don't need to lean on libraries, right? We don't need to just lean on the fact that linear algebra is multi-threaded in order to get our own things going. We actually have multi-threading built into Julia, and we can do this ourselves. And that's built into Julia using the threads module in base. And so this is accessed slightly differently than the modules that we've seen before with a dot threads, because it's a module, not a package. It's a built-in module. That's the only difference. It's just a slight difference in how the code is structured, which means that we just access it just slightly differently to say that I want to use the threads module instead of the threads package. That's the only thing there. So this is the module that exposes all of the core multi-threading intrinsics that we can use to multi-thread our code, including, of course, introspections to ask, how many threads am I running on by default? And in VS Code, as well as in Julia Pro, if you just start up Julia, by default, they will try to set the number of threads appropriately, and try to do this. As IDEs, they have access to Julia's launching process, and they can automatically start up Julia with the appropriate number of threads, which is a really nice thing to have happen and a really nice way of getting these all going. You can see that if I were to, for example, just pull up a Julia session in a terminal where I just type Julia and do the same sort of thing here. Let me make this bigger. So this is disconnected from my IDE, and I do the same sort of thing here using threads and threads. I only get 1. So this is something special that my IDE gives me, is the ability to automatically figure this out, this problem of how many cores do I have on my computer. If I'm not in an IDE environment, then I can just use this special -t flag to say, hey, let's use 6 threads. You know, this will set the number of threads for me like this. And then I get my 6 threads. And so eventually, in a future release of Julia, we'll move this into Julia itself to automatically spin up with the appropriate number of threads, I imagine anyways. For now, it's something that you either need to explicitly opt into at the command line, or automatically opt into in your IDE. Something to keep an eye on. So now that we have multi-threading going, oh yes, there's another way of doing it with an environment variable. This is how you would do it on Julia before 1.5. The -t flag is new in Julia 1.5. As in Julia 1.5, we've made multi-threading a stable interface now. So before it was experimental. Now it's a stable interface and you can do this. Oh, interesting. If you're seeing at your VS Code REPL, you're seeing only 1 thread. I wonder how, yeah. So I think that's in the extension settings here. If I go into, so I pulled up my extensions tab and click on the gear icon. You can go into extension settings, and I think this will tell you where you can set up threads. Let's see. Yeah. Oh, maybe it's something that I changed. Maybe I changed this at some point myself. It looks like, so this is blue, which means that I've changed this. And if I reset that, that might go back to 0 to 1 by default. Yeah, interesting. I'm sorry, I misled you all. Thanks for the comment. Yeah. Okay, so if you want to get 6 threads going in in your VS Code REPL, I guess it doesn't do this automatically. Julia Pro does this automatically. And I guess when I set up VS Code a long time ago, I changed this and totally forgot about it. My apologies to you all. I need to make a note of that for next time. So the way I did this, just to recap, I'll go back to this and start from scratch. So I was here in my notebooks. Oops, I closed the wrong thing. I'm gonna keep this open. So I was in my notebook. The way I did this is you can open up your editors pane and it'll by default show you your Julia editor here. So click on the boxes, the Julia editor, and then there's a manage gear icon thing that you can click on and go down to extension settings. This will pull up a settings tab and you can add in your search here threads. And this will pull up this setting that I've changed that you can set appropriately to the number of threads based upon what HWLoc or what you think is the appropriate number of threads, the number of cores that you have in your computer. And then once you do this and change this, you'll need to restart Julia. You can close your REPL and start a new REPL, and then that'll apply the changes. Thanks for saying that. My apologies for steering y'all wrong initially there. So this is not an automatic thing. And do this. So if you have a 6-core machine, use 6 threads. That's the simple answer. There are some cases where oversubscribing the number of threads to the number of physical processors that you have or physical cores that you have can be advantageous. But as a general rule of thumb, just use the number of threads that you have available that are the number of physical cores that you have. And again, you can access that by going up to the HWLoc package, asking for the number of physical cores. That's probably the easiest way to do this across all packages. So yeah. Okay, so hopefully now we'll have using threads and you'll see end threads as being set to 6 or whatever is going to be appropriate for you all to be using on your own computers. You can, explicitly start. So this line of code here, this will be one way of explicitly starting a Julia session that will change the number of threads. This will only work on Mac or Linux. Sorry, Windows folks. But it's just a little demo of, changing the number of threads at runtime based on either a environment variable like this, or with that -t flag that I showed. You can do it either way. And this will just spin up a new Julia process that will, have 4 threads or maybe -t 3 threads or something like that and print out the number of threads like that. Very simple way of just kind of showing this. This is, using a Linux or Mac command line. Unfortunately, doesn't work on Windows, but it's just a little demo. You don't need to worry about it if you're on Windows. It's just a little demo. So, in Julia Pro, it'll set to choose the good number for yourself. In VS Code, it doesn't do this yet. I should submit a bug on that. They should do that smartly. They know this. They can do something smart. Julia will eventually do the smart thing here too by default, but it's just tricky to make sure that it can be backwards compatible. Okay, so you've seen that we have 6 threads. You can ask what thread are we currently on, or what core are we currently on? So we're currently on thread number 1. If you get an error that says end threads is not defined, that just means that you need to do that using .threads in order to bring it into your namespace. And this will bring in that architecture. This is what you're missing. So yeah, using .threads is the key thing to bring in all of the threading architecture, including end threads, and then as well as thread ID, which tells me which thread I'm currently on, right? And so if I were to write a simple for loop here, and I create an array that has 6 elements, the number of threads. So I have, on your machines, you might see 4 elements or something like that. It's just an integer here. And then I go through, loop over from 1 to my number of threads and set that index to my thread ID. I'll get out all 1s, right? By default, Julia won't multi-thread for loops, right? It won't split this up. It'll run this sequentially as we're used to knowing, go through iteratively on a single core, just walk my way through all 6 things. And even though I kind of have this set up using thready kind of terminology from 1 to n threads using the thread ID, all 6 of my values here are set to the number 1. But just like the SIMD macro, we have a threads macro that will automatically split apart my iteration space and split it across my number of threads, assign each thread to do 1 chunk of my algorithm, and give me my answer back. And so if I redo this for loop, but this time prefix it with this special threads keyword, then this will allow you to split apart for loops across multiple threads. Kind of like how the SIMD macro said, hey, everything that we run in here is okay to rearrange to run on a single core so that we can do vector arithmetic on it. This does the same thing. It says, hey, the body of this for loop can run simultaneously across all of your systems. So there's a question about this, all caps Julia num threads. How does that work? So that's not Julia syntax. That's kind of a shell syntax. This caps Julia num threads. Simply setting this at Julia isn't going to change my number of threads. This is just defining a Julia variable. If, however, you define this as what's called an environment variable on your system, so like on Windows, this would be where you go into properties and set all those environment variables. I don't know if you've ever done that. It's like a system-wide setting that Julia can read to do this when it starts up. And so you can't change this dynamically. Julia can't, at this point anyways, dynamically change the number of threads. You need to shut it down and start it back up again. And so in order to get 6 threads in VS Code, that's where we were going to our extensions, changing how VS Code starts up Julia to, set the Julia number of threads by searching for the setting that has threads to the number that you want here. So that's the workflow to get into setting this to, hopefully you'll see a set number of threads that way. Okay, so this is our first multi-threaded for loop here, right? We've gone through, and it's very basic, but we've simultaneously set each of these 6 values to its thread ID, and we did that multi-threadedly. And that's pretty straightforward, right? That's awesome. That's easy. So let's go back to, for example, like our SIMD example where we were using sum, and let's, instead of using SIMD, let's use threads to split it 6 ways, give ourselves a 6-fold speed up. And let's do this just kind of the way, in the last example, we had SIMD here, right? This was how we did our SIMD sum. Well, we can just change that to threads and do this and evaluate this and run with it, right? Hopefully, maybe. Let's evaluate this, run this, and let's use an even bigger vector this time with 10 million elements. We'll run threaded sum 1 here, and that's interesting. And we can time our output, and it takes a really long time. It's allocating a lot, and it's giving me a number that's kind of strange, right? With 10 million elements uniformly distributed between 0 and 1, I would expect to see an answer of 5 million. And in fact, if I ask Julia what the sum of A is, sure enough, I get 5 times 10 to the 6th, or 5 million. But my threaded sum is giving me an answer of 833,000. That's odd. And it's taking a long time too, right? If I time how long it takes to do my sum, it's taking on the order of 5 milliseconds. But my threaded sum, my swanky multi-threaded algorithm here is taking 300 milliseconds. That's devastatingly slow. So not only is it giving me the wrong answer, it's giving me the wrong answer and it's taking a lot of time. So that is a problem, right? And maybe you can start seeing where we're going wrong just by looking at the answer that we're getting, right? The answer that we're getting, we want to have something around 5 million, but instead we're getting something that's 6-fold smaller. And I happen to have 6 threads. So that's pretty telling, right? That just like before, we can kind of use the answers that we're getting to kind of figure out what's going wrong here. And well, let's look at our for loop here. Well, this threads macro is promising to Julia that, hey, this body can be run at any point simultaneously across multiple threads. The multiple threads can do this across at the same time. And we're using a single bucket here, right? Our result bucket, we have a single bucket. And we're adding into it. Well, what does this plus equals operation do? Well, it's actually just reading what the value of R is, adding some element to it, and then storing that same value back into R itself, right? This result bucket gets read from and stored to, and these are 2 separate operations, right? We have 2 separate operations that are happening here. We read from R, we're adding our element out of A, and we're storing back into R. Of course, we can grab into the elements of A nicely and multi-threadedly, right? We have all 6 of our threads working at different sections of our vector at different points. But if they all are reading and writing into the same memory location at the same time, that's going to be a problem. And sure enough, that makes sense, right? Why are we only getting 1/6 of the total that we would expect? Well, if you think about 6 threads simultaneously reading from our bucket, they all simultaneously read from our bucket. They all add their current value, their current index that they're working on. And then they all store back into R at the same time. They all take their own little limited view. Well, only one of those 6 is actually going to take effect, right? Only one of those 6 values is going to propagate to the next for loop. And so essentially, this is a canonical race condition, as they're called, where we're racing to set this bucket by all 6 threads. Only one of those 6 threads is winning on average. And so we end up with 1/6 of the results because 5 of them get overwritten in the time that it takes to read the next answer out. And so when each thread goes back to read the next value, it's only seeing the update from one thread. So we only get 1/6 of the answer, which then also means that all of our processors, all of our cores need to cooperate amongst each other in order to synchronize their accesses and reads. Even though they're overwriting each other, they're all trying to write to the same memory location, which must be sequenced out. And essentially, we're telling Julia to do an operation that is nonsensical here. And it unfortunately happily does this for us, unlike SIMD, where this would just fail to work, right? It would just fail to happen if it can't do it safely. Here, not only did it happen, it gave us the wrong answer, and it was slow. So there are 2 nice things about this problem. One is that there's 2 ways that we can identify this. Often, if you have a race condition, it ends up slowing down your algorithm instead of speeding it up, which is kind of a nice little canary in the coal mine to look out for. And then, of course, the wrong answer is another thing that you can use to make sure. So often I start with a serial algorithm and make sure that I end up with the same answer in my parallel algorithm. So that didn't work. And it was because we were reading and writing at the same time, or our reads and our writes were separated, right? It's because our reads and our writes didn't happen exactly at the same time. So there's lots of ways of working around this problem. And if you're familiar with other languages, there are techniques that you can use to synchronize these things. One such technique is what's called atomics. And the language here comes from, the smallest indivisible thing that can be used. Unfortunately, our most used version, that's the true meaning of atomic, right? It's the smallest indivisible element. Unfortunately, due to history, we use that word for something that ended up being able to be split in the end, right? Atoms themselves can be split. When atoms were named atoms, they were unsplittable, right? We didn't know that atoms could be split when we named atoms from chemistry. And so often, the first thing that you think of when you hear atomic is you think of nuclear weapons, which is splitting the atom. But the core meaning of atomics means that it can't be split. And so computer science uses the language of atomics to describe an operation that can't be split apart, that must happen jointly. And so we can restructure our algorithm in terms of atomics, for example, in order to get this working thread safely. And you can do this, right? We can have threaded sum 2, and you execute this, we'll get the correct answer now. So phew, we got the correct answer because we're using this special atomic syntax. We're using this special atomic syntax. You don't need to know this exact syntax because this isn't going to be the final state here. But it is this inseparable operation where we read from and write to R at the same time across all of our cores. But that means that all of our cores are still accessing the same memory element, which means that behind the scenes, they still need to sequence these reads and writes, these indivisible reads and writes, into a serial operation, which means that we're not going to see a speed up here of our threaded sum. In fact, it's going to be yet slower because of all this synchronization that needs to happen. We've expressed our algorithm in a way that can't be split in a thread-safe manner, but it's meant that we're leaning on Julia to implement this and to sequence out our structure to be able, so each thread reads, blocks all other cores from reading at that time, then writes, and then allows all other cores. So while we're using 6 cores to do this, they're needing to coordinate their operations. And so that is not going to be their final solution here, but it gets us to the point of, how you can start thinking about, this is breaking our traditional understanding of how computers work. So that gives us the right answer, but it's still slower, right? And there are other ways of doing this, and that's where we'll pick up tomorrow. I think now is a good place to stop, kind of with this puzzle about how can we do a threaded sum that actually uses all 6 of our cores, or however many cores you have on your machines. And that's where we'll pick up tomorrow, since we're running out of time, just a little bit behind schedule, but I think we'll be in good shape for tomorrow to start off. And so just as a reminder to everybody, tomorrow, we're going to go into other forms of true parallelism, including distributed compute and GPU compute. In order to make the most out of those classes, we're going to lean on cloud computation to spin up cloud computers that allow us to submit jobs to our cloud compute to allow us to run code across many workers, spin up lots of workers, as well as spin up workers that have GPUs attached to them. And so we'll use Julia Hub to spin those up and to enable you all to have access to some of this compute resource. Just a reminder to send me your emails. I know lots of you already did at the last break, but before you sign off today, please send me the email that you used to log in to Julia Hub, and we'll enable compute for you. So again, go to juliahub.com, log in here and set up an identity either with email or with an open authentication mechanism that pings some email, and we'll enable this access for you tomorrow, so that way we can use Julia Hub for some compute. And this will be particularly important when we talk about GPU computation, because I'm wagering the vast majority of you do not have computational GPUs attached to your machines. I have a fairly recent MacBook and it doesn't support this. Some machines will, and if you do, that's awesome. You can play around with how that works, but a lot of machines don't, and so we'll spin up a machine in the cloud that can allow us to look at GPU compute. So if you want to send it to my email address, you can do that. I'm at mbauman@juliacomputing.com. You can do that, or you can, PM me the message on Zoom group chat here. Just send it to me privately by selecting my name, or if you don't care about folks seeing your email address amongst the 15 of us, you can just put it in the chat to everybody, of course. And I'll grab those, send that to our dev team, and enable compute for you all. So that way you can do that. Yeah, exactly. 15 new friends can email you. I have a gazillion new friends this fall from all the political campaigns in the United States, sending me thousands of emails. So I don't know that 15 more friends. You all are much better friends than politicians are to me. So feel free to email me. Thanks so much for all your attention. I'm happy to stick around for any questions at the end. One question that I hadn't addressed, but it looks like one of you did that about, Unicode access. We can talk a little bit about. So we have LaTeX-like auto completions just by typing / and then some LaTeX-like command and hitting tab will autocomplete to Unicode characters that you can actually use in real code. So like x1, you can just type x and then / _ 2 and then hit tab. That'll autocomplete to this. And if you're ever wondering, you see some fancy gibberish and you're wondering, how in the world do I type this crazy letter? Well, you just type help and then paste it into your help REPL. And even if there's not documentation assigned to this, right? I've not defined anything to this crazy Greek letter named Xi. I can just ask for help, paste it in, and it'll tell me how to tab complete this by typing / xi tab, and it'll type this crazy Greek letter. So this applies to Greek, it applies to superscripts, subscripts, all these things, even complex combinations of, x cubed, or you say chi squared, right? You can ask for help on these things and it'll tell you exactly how to type them. Fun little thing with Julia. I'll stick around for the next 5 minutes if anyone else has other questions about any of the things we covered today. Tomorrow, we'll dig in more to true parallelism across threads, distributed compute, and GPU compute. And I think we should be in good shape. We might cut short our parallel algorithm design lecture a little bit just to make sure that we have time to talk about all the fun things of doing compute on Julia Hub. But thanks everyone, and I will see you all in about 20 hours, wherever that may be in whatever time zone you may have. So good evening, good afternoon, good morning, good night, and see you all later. So a good question from Jean-Philippe about cloud computing and how can you know in advance the number of threads? That's a good question, and it extends not just to the number of threads, but the number of computers that you have access to, right? If you're spinning up multiple nodes in a cluster, how many nodes are available? How do you know how many of these things should there be, and how do you get them all set up that way? Well, the short answer is that it doesn't matter too much. And we've tried to structure all of Julia's parallelism intrinsics in ways that it doesn't matter how many ways you split this up. So, take the threaded sum that we finished with here. It's not the final state of our multi-threading, but you've noticed that I didn't say across 6 threads, for example. Nowhere did I write 6 threads, but Julia will automatically detect how many threads are available to it and how many threads it was started with. and split up my iteration space across all of those 6 threads. And so the only tricky part is really in spinning up Julia once you're on your cloud machine. And that's taken care of in large part by the infrastructure you're using. And hopefully, whatever infrastructure you use will automatically start Julia with the appropriate number of threads. So that way the intrinsics you use will scale, be it on a 2-core machine or a 64-core machine. The code that you write doesn't change, but the infrastructure will automatically launch it with access to the appropriate number of threads. And I'll show you tomorrow how to do that with Julia Hub. And we'll see how that looks. And it's kind of an infrastructure question and not a code question, because the code we try to write in a agnostic manner. So it doesn't matter how many threads are connected to your Julia session, and it doesn't matter how many nodes or how many compute workers or how many different boxes are connected. It will automatically elastically scale your algorithm design. And so we'll talk. The first lecture tomorrow after we wrap up threads will actually be on parallel algorithm design and ways in which you can write algorithms that are thread safe. They don't have this kind of race condition here, and they can scale to arbitrary numbers of threads. So that'll be the first lecture after we wrap up multi-threading tomorrow. So hopefully that answers your question there. Now I get to go through the chat session and harvest all these email addresses. Thanks everyone for sending them. So I'll stick around to copy and paste all these email addresses back out. And while I'm doing that, feel free to ask any other questions. And when I see them, I'll happily answer them. But let's do that here. Yeah, you're all free to go. See you, Vish. That's a good question. So sorry, I just noticed this now. So you're asking about there are some times where I didn't use the $ and it didn't change the time. The answer there is that in general, the overhead on that dynamic lookup is on the order of 20 to 50 nanoseconds a loop. So that's the meta question of asking what is this type and how do I do it? It only needs to ask that once, and then it goes into doing the find closest algorithm. And then once it's inside there, there's a lot of overhead in lots of other meta questions on the elements, right? And so you're just adding one small meta question on top of a already de-optimized problem, or a poorly optimized problem. And so that overhead, it's there, it's just so small that it's inconsequential at that point. And so sometimes if you're using large data structures or measuring things that take on the order of hundreds of milliseconds to complete, you won't see a difference between the $. But it's kind of good practice, and you're right, I should probably make sure that I use that consistently, but you won't see a difference in places where you're benchmarking large kernels or large chunks of work. Thanks for the question, and thanks for all the questions today. I'll see you tomorrow. Andre, Amit, Dylan.